All right, we are ready. Okay, people made it to the last day. Yay. So today's session is going to be all about galactic transients, something that I think is not stressed enough how rich of a data source Rubin is going to be for things that are erupting in the galactic plane. Our first lecturer will be Mike Shara. Mike is currently at the American Museum of Natural History and jointly at Columbia. Mike got his undergrad at Toronto, then went on, undergrad at Toronto, then PhD at Tel Aviv, and then was an astronomer at Space Telescope before moving to the New York City area. Mike, as you'll hear, Mike works on a lot of phenomena related to Novae and accreting binaries, and he'll tell us today about Novae eruptions and in the context of LSST. One quick reminder, so for the second session today, we will be having this quick one slide presentation from you all. And I saw that most people uploaded, which is great. Thank you. If you haven't uploaded yet, you have 1.5 hours to do so. Please have a slide uploaded so we can, walk through the this quick 2 to 3 minute presentation about what you're excited about the most to do with the LSST. Okay, take it away.
All right. I've been tasked, well, kind of double tasked. Unfortunately, Jenna was not able to be here, and that's really a pity because she's both a wonderful speaker and a terrific astronomer. So I'm going to try and take on some of the stuff that I think that she was going to do, particularly with regard to symbiotic stars. So I've latched on a piece at the end. I also thought she was going to do the galactic, that is the novae that go on in the galaxy and the populations within the galaxy. But of course, Kishole has made such fundamental and important contributions there that I can't really add much to it, but I'll mention it en passant. But what I really am going to focus on are a couple of things today. I'm going to focus on novae, the explosions of novae, less so how they get there, that is the evolution of the binary stars. You've probably seen these little binary diagrams, these flow diagrams over and over for the last 2 weeks to the point that you're sick of them. So I'll just show you one, okay, that really is how stars get there. I'm going to spend some time talking about both their physics. I'm going to talk about searches for them in other galaxies, including very briefly an ongoing one that Alexandra and I are involved in. And then finally, a little bit about symbiotic stars and just whisper the term type 1a supernova towards the end. So that's what an overview of today's lecture is going to be about. Nominally runs 90 minutes. I will not be at all insulted if someone goes whipping out to the bathroom or whatever during that time. If you prefer, I can take a 5-minute break, maybe 30, 40 minutes in. We'll see. Let's just play it by ear. And please, if I say something dumb or unintelligible, pick up your hand, wave your hand, ask questions. Okay, I want this to be two-way if at all possible. And let's see if I can get my computer. There we go. Okay. So, like I said, talking about what are novae, binary evolution, the so-called hibernation scenario of cataclysmic binaries, which today I respectfully suggest is the best long-term evolutionary scenario that we have. It's far from complete. There are still observational and tests as well as numerical simulations that need to be done. Nevertheless, I think it's moving in the direction of where we're going to have a complete theory of novae, well, a more complete theory of novae in the coming 5 to 10 years. I'm going to talk about the recovery of a particular nova, the nova of 11 March 1437. And what it teaches us about the connection between dwarf novae and classical novae. Then show you some of these self-consistent simulations of novae, the hibernation scenario, extragalactic novae with Hubble, and then yesterday I tacked on symbiotics, a very short summary of symbiotic stars also at Kishole's request. So why do we care about them? And why are they right at the tail end of the transients? Okay, these low energy guys, less interesting than the other transients? Oh, au contraire. Yes, they're the fourth brightest explosions nominally after the Big Bang itself. Supernovae and gamma ray bursts. Maybe there are very rare brighter events also. They certainly are major sources, probably the major source of nitrogen, maybe of lithium in the universe. They used to be thought of as great standard candles out to 100 million light years. We're all much less certain of that today, mostly because of the work that was all inspired by Nancy Kaslowal about, I guess, 15 years ago, when she found what are called faint fast novae in the Andromeda Galaxy. And that sort of put people on the back step. And I've now found a bunch of them in M87. They're a significant fraction of the nova population, and they produce a tremendous amount of spread at the fast end of the T2, the decline time, the absolute magnitude decline time relation. So they're probably not very good standard candles, you know, plus minus a magnitude kind of thing, but they're never going to compete with Cepheids. They're never going to put the tip of the red giant method out of business, nothing like that. Are they progenitors of type 1a supernovae? Well, this is something that's argued and debated in the literature over and over and over again, and I'm not going to spend a lot of time on that. The answer is probably yes, and I'll give you just a little bit of an idea of what we think is going on. And finally, they are actually wonderful tests, and maybe the most useful thing that they do for us is allow us to make really concrete predictions from binary population synthesis about how many novae and what kind of novae should exist in galaxies. And since these are relatively common, you get of order 50 to 100 novae per year in a big galaxy, maybe 70, you get over 300 per year, one a day. It's not like supernovae where you see one a century or a couple per century in a galaxy. So because they're so much more common, or 1,000 times, you know, nice rule of thumb is there's 1,000 novae for every supernova. You can do statistical tests on them that you will not be able to do, I think, for a long time. LSST is going to help us, going to make a big difference in being able to collect huge samples. But we can still do better modeling on binary population synthesis with novae. So these are the reasons for studying. So what have I and other people used for decades? Well, we're opportunists. If we can only get a 1 meter telescope, we'll use a 1 meter telescope. If we can get an 8 meter class telescope, we will. Hubble has made a huge difference. I'll show you some results from the Hubble telescope that have really changed the way we look at the numbers and the rates of novae in extragalactic systems. So let's go right back to basics. Binary stars. There are only 4 kinds of binaries possible. You've either got a detached pair that neither star fills its Roche lobe, or you've got a semi-detached pair where one of the stars fills its Roche lobe and starts to transfer mass. Contact binaries where both of them fill their Roche lobes, and common envelope systems or rapidly mass transferring systems where you both overfill your Roche lobe. So that's all there is. And the systems I'm going to be talking about today do this. It's really important to understand when you think about novae and cataclysmic binaries that there are times when nova systems do this, and this is what we're used to seeing them do. But I'm going to try to convince you that they also flip over to that and then back and forth, back and forth, back and forth on different time scales, up to centuries, millennia, maybe even 1 million years in some cases. And that flipping back and forth accounts for the huge diversity. I mean, cataclysmic binaries, novae, dwarf novae, recurrent novae, magnetic CV. I mean, there's a zoo of these critters. A lot of the strange behaviors And the fact that you can get such wildly different looking systems that behave the same way is just because of this. This is the key to understanding, or one of the keys to understanding cataclysmic binaries. So novae themselves are all mass transferring binary systems containing a white dwarf, and they are roughly 1 star in 1,000 of that order. So relatively common, okay, not all that rare. There is no question but that they must have undergone at least one common envelope interaction during their lifetimes. There's just no way around it. So in the most vanilla flavored system, you've got a white dwarf sitting at the center of an accretion disk, and it is cannibalizing its sun-like companion or its red giant companion. Up until a few weeks ago, the question.
Sorry, you said that novae are 2 types, the semi-detached binaries and the detached binaries. But now you said that all novae are mass transferring, but in the detached binary case, there is no mass transfer.
Correct.
So is that just that it's the first step before it's semi-detached, or how does that happen?
Good question. Excellent question. So let me back up. Oops, that's the dreaded diagram. I wasn't precise enough. The systems that we observe, the ones that are bright, are the ones that are bright, okay? And the ones that are bright are transferring mass, because mass transfer means that you have stuff smashing into an accretion disk, flickering, accreting onto a white dwarf. These are the things that make light and so call attention to themselves, okay? I'm going to try to convince you that nova eruptions can push you to this state. Counterintuitive initially, but it's a true statement. And the length of time that you sit there can be very long. And if it's very, very, very long for some systems, then many, many systems can pile up there and hide, okay? So the systems that we're used to seeing, the so-called nova-like binaries and the dwarf novae are all here, these kinds of systems. But I'm gonna propagandize you that most cataclysmic binaries are these systems, and they're in deep hibernation. Barely have a heartbeat, okay? No mass transfer, virtually none. Thank you, good question. So when I say all novae are mass transferring white dwarf binaries, they're all mass transferring white dwarf binaries at some stage in their lifetimes. And they have to be mass transferring binaries because you've got to get hydrogen onto the surface of a white dwarf. If you don't have anything sitting on the surface of a white dwarf, you don't have the fuel to get the runaway nuclear burning that you need to make a nova. So you've got to have a contact button. You've got to have your donor star, your hydrogen-rich star, usually, in contact with this Roche-load. It is also possible to have 2 white dwarfs, where one of them, the less massive white dwarf, usually helium white dwarf, fills its Roche-load and transfers helium onto the surface of a companion star. And if you put enough helium on the surface of a carbon-oxygen white dwarf, it will become degenerate enough also to explode, okay, as a nova, but where you have a helium thermonuclear runaway. It's going to be a lot more violent. All sorts of other interesting stuff can happen. But the vast majority, okay, of known systems are these. There's 1,000 known of these in the Milky Way, and only one of these that really is reasonably well seen. And I wrote here either a sun-like star or a red giant. The so-called symbiotic stars are the ones, the symbiotic novae, have the giants. Sun-like meaning a GK or an F-type star. Until a few weeks ago, there were no A or B companions known. There is now apparently a very good B type main sequence star, a B1 dwarf, sitting next to a white dwarf that about 3-4 years ago underwent a nova eruption, and people are starting to realize, yep, we can actually get these really rare systems. So anything that fills its Roche lobe and transfers hydrogen onto a white dwarf, in principle, can make a nova. This is the evolutionary pathway. I'm sure you've seen this over and over and over again, so let's just quickly go halfway down. You start with a couple of main sequence stars, one of them that are far apart, okay? They're not contact binary, anything like that. You've got to allow enough time to turn the core of one of those stars, and they've got to be far enough apart that the core of one of those two stars turns into at least a helium, preferably a carbon-oxygen white dwarf. You get a common envelope phase, loss of the common envelope, and you emerge with a white dwarf and a main sequence star that have to be pretty close together if you're going to make a nova. And at some point, gravitational radiation or angular momentum losses through a wind or some other mechanism brings the stars close enough to each other that one star does in fact fill its Roche lobe and start transferring hydrogen via an accretion disk to make a cataclysmic variable. And then there are various pathways in here to lead to either double degenerates, to white dwarfs, or to type 1a supernovae, and I'm not going to discuss those in detail today. But you do need a common envelope phase. That's the key thing to get a white dwarf within about 1 solar radius of a main sequence star, because the white dwarf at one point was the core of a red giant, which had a radius of 100 solar radii. So you have to have gotten them vastly closer together. The only mechanism we know of to do that, other than some advanced interstellar civilization, is to have a common envelope at work.
What is the mechanism that drives the outflow of the common envelope? Is it radiation pressure?
So, are you a chef? Do you know how to make a souffle? Okay, no, so if you have an egg beater, imagine an egg, put a couple of eggs, separate the whites and the yolks. Take the whites, the albumin, put an egg beater into it. You froth it all up. Okay, you're transferring energy and angular momentum essentially to the albumin. That's what happens in a cataclysmic binary. You have the one star enveloped by the expanding envelope of a red giant with a white dwarf at its core. So you have an object moving at hypersonic speed, typically 10 times the speed of sound inside the envelope of the red giant. Anything moving at 10 times the speed of sound inside anything else is going to generate a shock wave. That shock wave is going to transfer energy into the envelope and help drive the envelope away. Okay, you're just mix mastering, you're egg beatering the outer envelope of the red giant. It flows away. At the same time, you're transferring energy and angular momentum into that envelope, losing it from the binary. And so the stars are going to approach each other. The core of the red giant, namely the white dwarf, and the companion that is inside it are going to be brought much closer together. That process doesn't have to work every time. It only has to work, one case out of 10, 1 out of 100. And population synthesis models wave their hands hardest when they talk about common envelopes. That is one of the most poorly understood steps of stellar evolution, of binary stellar evolution. And that's because the interactions are happening, all the interactions are happening on a dynamical time scale. Things are changing in tens of seconds or hundreds of seconds in your grid points, but you've got to follow this process for tens of 1,000 years anyway to watch it completely evolve. So it's very difficult to calculate from first principles, but we understand that must be what's going on. So that I think that's the answer to your question. A bit long, but. Okay, let's consider the equipotential surfaces of a binary. Just imagine your rubber sheet here, and you put a heavy cannonball here and a light cannonball over there. You've got two dips. If you're a particle, okay, a zero mass particle, and you're deep inside this potential well, but you manage to get up to the edge here, where are you going to go? Well, you're going to fall into that hole there. That's the case where one star fills its Roche lobe, the main sequence star. The other star, the white dwarf, does not fill its Roche lobe. That's generally what happens. And the separation between the two here is fixed, but in fact, that separation can and must change because the shapes of the Roche lobe are entirely determined by the masses, okay, of the two objects and their motion with respect to each other. But if you blow away some of the mass, which is what a nova does, then the force of gravity between the two stars, okay, GMM over R squared, is going to go down. And if you blow that mass away, basically spherically symmetrically, the two objects are going to move further apart. So at least in principle, you expect the two stars in a nova binary to separate during a nova explosion by some amount. Okay, we'll come back to that. The power source for a nova is just, you know, plain old fusion. Inside stars, you take hydrogen, fuse it into deuterium, helium-3, helium-4, and this makes up 90% of the power source for most stars. Another 9% comes from helium fusion inside stars. That all goes on deep inside the cores of stars, okay? So you've got equilibrium, you've got hydrostatic equilibrium. While this produces a vast amount of energy, you've got tremendous pressures pushing outwards. You also have the outer layers of the star pushing inwards and hopefully holding everything stable. In the case of a nova, that's not true. And the reason it's not true is that the equation of state is not that of a perfect gas. P is K over mu H rho T throughout most stars. The pretty good first approximation. But in the case of degenerate hydrogen on the surface of a white dwarf, the pressure goes like rho to the 5/3. It can be somewhere between 5/3 and 4/3, depending on how degenerate or how relativistic degenerate the gas on the surface of the white dwarf is. But the important thing to note is that once you have hydrogen sitting in an envelope on a white dwarf, it's governed by this equation, which is temperature independent. Why is that important? Well, you have nuclear reactions. Nuclear reactions release energy. Energy means that the temperature in the envelope, the accreted envelope on a white dwarf, rises. The temperature rises, but the pressure doesn't care. Okay? Pressure only depends on the density, and the density isn't changing. So the nuclear reactions go faster and faster and faster and release more and more and more energy. The envelope doesn't budge, doesn't care. Okay? Until you get so hot that electron degeneracy is relieved, at which point you flip very quickly back to the perfect gas equation, and then the gas on the surface of the white dwarf says, oh my God, there's enormous pressure. I'm way out of hydrostatic equilibrium. And the gas starts to expand like crazy. That's the cause of a nova. It's the underlying cause. It's because you flip from an electron degenerate equation of state to a perfect gas equation of state in almost no time. Andrew.
Does this mean the convective envelope is changing in radius in some way if the temperature isn't changing?
While you start with a hydrogen envelope in place on the surface of a white dwarf, and a nice analogy in terms of size is that white dwarf is about the size of the Earth. The hydrogen envelope you accrete is about the depth of the Pacific Ocean, a couple of kilometers. That's all you need. At that point, the pressure from the outer layers of the hydrogen onto the lower layers of hydrogen, onto the bottom of the Pacific Ocean, is high enough that nuclear reactions will proceed even at zero temperature. Picnonuclear reactions will go on. They make the hydrogen hotter and hotter and hotter and hotter, but there's no change in the pressure, and so there's no change in the structure of the envelope until you reach 50, 60, 70 million kelvins, at which point convection is going, and the nuclear reactions are now proceeding on a time scale of seconds or tens of seconds, okay? And so you release a vast amount of energy, basically the binding energy of the whole envelope in just a minute or two, very short period of time, at which point the envelope is no longer electron degenerate. It feels that pressure, it feels the vastly increased pressure, and there's nothing sitting on top of it to hold it down. So away it goes. That's really what that's all that a nova is. So it is a thermonuclear runaway in the electron degenerate envelope of a white dwarf star. And once the degeneracy is relieved, boom, the envelope gets ejected. I'd like to say on a time scale of minutes is not quite that simple. The entire ejection can take months. It depends very much on how much mass was there to begin with, how large the white dwarf is. The lower the mass of the white dwarf, the greater the radius, the lower the surface gravity, the longer it takes for the envelope to escape. Okay, so there are various relations. But all the interesting action happens in just a few minutes. That is, all the thermonuclear energy, or the vast majority of it, is released in just a few minutes. So here's a little movie which may or may not work. It is of a CV in action. The orbital periods of cataclysmic binaries, the large majority of them, are just hours. Okay, they could be as short as 90 minutes, as long as a day or two. If you have a subgiant, it can be 2 days. And if you have a giant companion, then the orbital period, the separation between the stars, then of course has to be about 100 astronomical, about an astronomical unit, not a solar radius. And then the orbital period can be as long as 1 to a few years.
You always expect there to be a disk, and maybe the answer is yes for the close binaries, but what about the symbiotic stars?
Yep, so I'm
Okay,
that's
sorry.
about 40 slides further on. So the answer is yes, you expect there to almost always be a disk, or there to be a disk, and the accretion is via a disk as long as the white dwarf is sort of a run-of-the-mill white dwarf, not a strong magnetic field. Okay, then the accretion is just like I showed you. Whoops, back. All right. The accretion is via the stream into a hotspot that glows and flickers. That's why CVs flicker on time scales of seconds. And loss of energy and angular momentum allow material to drift in through the disk and eventually settle on the surface of the white dwarf. So that's the vanilla flavored system. I didn't emphasize that here, and don't even have a slide for it. But if you have a magnetic white dwarf, and that may be 25% of all systems, where the magnetic field is strong enough so that b squared over 8 pi, the magnetic pressure of that more or less dipolar magnetic field, balances the pressure in the disk, in which case the plasma in the disk will be trapped by the magnetic field and flow onto the poles of the white dwarf, okay, instead of onto an equatorial ring around the white dwarf. So the accretion can be different. The surface gravity on a white dwarf is vast. There are no mountains, there are no hills on white dwarfs. Probably the highest waves that run around the surface of a white dwarf are never going to be more than a few millimeters high. That's a vast tidal wave on a white dwarf running around a white dwarf. So in some sense, it doesn't matter vis-a-vis novae. That is, you accrete matter either into a ring around the belt, the equator of the white dwarf. But if that belt gets a few millimeters higher, then the rest of the surface of the white dwarf, matter will flow away and coat the surface of the white dwarf. So we don't expect there to be huge differences. Just because we don't expect it doesn't mean it doesn't happen, but probably not. It is certainly going to be true that the accreted matter, whether in a ring or whether it piles up a few millimeters higher than the rest of the star at the poles, the thermonuclear runaway is going to start somewhere. You're never going to have the temperature identical around the surface of a white dwarf to 1 part in 10 to the 10, or even 1 part in 10 to the 4th. So you can have differences of just a few hundred degrees Kelvin over the surface of the white dwarf. And that means that when a thermonuclear runaway starts, it starts in a particular place on the white dwarf. And both advection, convection, 3D funny effects that are being calculated by Jordi Jose and others will eventually bring the thermonuclear runaway around the surface of the white dwarf. So it doesn't really matter whether it's via an accretion disk or via magnetic field that you funnel the matter onto the white dwarf. At least that's the conventional view. And maybe one of y'all will show that that statement was false. It's possible. Did I answer your question? So there's the accreting white dwarf. It's got a Pacific oceans of hydrogen, as I said. Density at the bottom of this metallic hydrogen ocean is about 10,000 grams per cubic centimeter. Temperatures reach 80, 90 million, 100 million. And that's when things get really interesting and stuff starts getting blown off the surface of that white dwarf. So you can think of a nova as a 10 to the 16 megaton hydrogen bomb. It reaches between 100,000 and 1 million times the sun's brightness. We've seen novae, we have detected novae erupting 100 million light years away with the Hubble Space Telescope. Typically, it's 10 to the -5 solar masses of a hydrogen helium ocean that's ejected, and typically at about 1% the speed of light. So it's the poor country mouse cousin of the supernova, okay? It's much less energetic, but it goes off, these things go off 10,000 to 100,000 times during their lifetimes. Okay, so they go off over and over and over and over again. They're not a one-time flash in the pan. What happens to the white dwarf? The answer is almost nothing. You can think of a nova eruption as kind of mowing the grass. Okay, the grass grows back, or giving the white dwarf a haircut. More hydrogen is going to fall back onto the surface from the companion star, and it'll go off again. Now, there's 2 questions you can immediately ask. What's the time between nova eruptions? Okay, we know that they must go off many, many times. Well, sorry, I should step back and say, how do we know that? I didn't include a slide. Beautiful paper by Holland Ford in 1975. Holland pointed out that there are, at that point, it was thought there were 25 novae a year in the Andromeda galaxy. Now we know it's at least 50. It might even be 80 or 100. If you get 100 novae going off every year in the Andromeda galaxy, and the Andromeda galaxy is 10 to the 10 years old, okay? 100 times 10 to the 10 is 10 to the 12. That means there's 10 to the 12 novae in the Andromeda galaxy, and that's as many stars as there are in the Andromeda galaxy. Therefore, every star in Andromeda is a nova. Okay, that's ludicrous. It's only 1 in 1,000. That means that novae must erupt at least 1,000 times. So it's that simple a chain of deduction. And we understand the mechanism. You blow the envelope off, the companion star will eventually fill its Roche lobe again, transfer hydrogen onto the white dwarf, and the process repeats itself over and over again. The white dwarf, we see this both in numerical simulations, and you can convince yourself on the back of the envelope, is unscathed. White dwarf doesn't care at all. The only thing that happens is that when the hydrogen settles onto the white dwarf and sits there, a little bit of hydrogen is going to diffuse into the white dwarf. A few meters, okay, out of those kilometers of hydrogen. And that means a little bit of the carbon-oxygen outer part of the white dwarf is going to be no longer pure carbon oxygen, but it's going to be 90, 80, 70, 60. Okay, there's going to be a change in the abundance of hydrogen versus carbon oxygen over a couple of meters. And that layer, it turns out, is actually very important in helping the thermonuclear runaway take off, because when you have a 50-50 mixture of hydrogen and carbon oxygen, then basically every carbon or oxygen nucleus during a thermonuclear runaway can capture protons, has enough food. Okay. Normally, in the carbon-oxygen white dwarf, in the outer envelope, you have no hydrogen. And so there's no possibility of nuclear reactions. And so the nuclear reactions would only happen outside, that is in the accreted envelope, which is only going to have 1 or 2% or 3% carbon oxygen, depending on the metallicity of the donor star. And if that's true, then you'll get a thermonuclear runaway, but you won't be able to match a key observation of novae. When you take the spectrum of the ejecta of novae and you measure the abundances of the CNO nuclei, in particular nitrogen, because everything gets turned into nitrogen during rapid CNO burning, you see that it's 10 or 20%. Nowhere else in the universe do you see 10 or 20% Z. Z is not 0.2, Z is 0.02. In anything in this neighborhood, in the Magellanic Clouds, it's 10 times smaller than that, little. But in the ejecta of novae, you see it's 20%. And the reason it's 20% is because a little bit of hydrogen has dribbled down into the white dwarf, just this far. That's all you need to do, just a meter or two. And that outer meter or two, which then participates in the thermonuclear runaway, gets ejected. And so the shave of the white dwarf takes a little bit of skin off also, just a little bit, okay? Over the lifetime of this process, you lose typically 10 to the minus 5 solar masses of hydrogen, and you take with it of order 10 to the minus 7 solar masses from the white dwarf. So over thousands of nova, tens of thousands of nova eruptions, the white dwarf will lose a few percent of its mass. But in first approximation, it will remain unchanged. About 20 years ago, I was lucky to participate in this beautiful set of simulations conducted by Ofer Yaron, who's now at the Weizmann Institute. Ofer, under the tutorship of Dina Prielnik, my academic sister, one of my best friends in astrophysics, did a huge set of simulations of novae, what were then the state of the art, and came up with this set of tables which tell you that as a function of the mass of the white dwarf, the temperature of the white dwarf, the accretion rate onto the white dwarf, these are the three free parameters you have. What is the maximum ejection velocity during the thermonuclear runaway? The maximum luminosity you expect, the amplitude and magnitudes in the binary system, the time scale to eject most of the mass from the nova, the mass loss time, and the recurrence period in years. So this was, at the time, the state-of-the-art set of simulations. It's been referenced many hundreds of times. And if you want to know roughly what the characteristics of a nova, the given white dwarf mass, mass transfer rate, et cetera, are, this is still the go-to place, but we're about to improve on that dramatically. So how do novae make hydrogen and, nitrogen and lithium? Well, the hydrogen goes in here. The slowest step in the process is this. Okay, so stuff piles up as nitrogen 14, and basically put 4 protons in, helium comes out. The lithium comes about because you do make some helium-3 and you have helium-4 there to begin with, and that will allow the decay to lithium here. So novae are non-trivial sources of lithium, but it's there's a great deal of debate going on as to whether your cell phone is powered by novae, whether the lithium in the battery really does come from novae or not. The answer is we don't really know. Nitrogen is one of the strongest emission lines in the ejecta of all novae. This is an image taken of GK Persei of the nova of 1901, taken by the Hubble Space Telescope in the 658 filter, and all of these filaments are extremely nitrogen bright. And really the reason is because 20% of the ejecta of the nova, very rough rule of thumb, is nitrogen. And that's because nitrogen is the slow step. Nitrogen 14 is the slow step in rapid CNO burning. So novae do produce much of the nitrogen in the universe. I had something else I wanted to say. Oh, we do have a velocity map coming from GK Per because we took images a few years apart. And so we were able to measure the velocity of each of these individual filaments in the ejection. They do show that it's not just a nice, smooth, spherically symmetric wind. Okay, stuff is coming off novae, and even if it were quite smooth at the beginning, there are instabilities of some sort, hydrodynamic instabilities, that are breaking up the flow into these long filamentary structures, fingers that mostly point backwards at the central white dwarf. So the flow is not completely trivial, and it's not a well-solved problem. Let me step aside for a minute and talk about dwarf novae. These are gravity-powered systems. So novae, classical novae, the eruptions of novae are thermonuclear-powered systems. Dwarf novae are gravity-powered systems. So again, you have a red dwarf, white dwarf, you have accretion, but there's no nuclear burning going on because remember, you've got to build up this Pacific Ocean's worth of hydrogen. You're only accreting hydrogen in most systems at a rate of 10 minus 9, 10 minus 10, 10 minus 11 solar masses a year. So it's going to take you thousands of years to actually build up to that critical level, that critical mass envelope that you need, typically 10 to the minus 5 solar masses to get a thermonuclear runaway. So what happens in the meantime? Well, it turns out that the accretion disks themselves can be unstable. There are thermal and viscous instabilities, maybe magnetic effects also, where the accretion disk builds up, matter doesn't fall on quite fast enough, matter gets denser and denser and denser. There is an instability, first postulated, I think it was by Osaki in 1974, which causes the accretion disk to go just to collapse very quickly on a time scale of a day. So you may build up the accretion disk for months, matter will flow in, but it will still build up and then boom, collapse in just a day or two onto the surface of the white dwarf. And that's going to give you about 100-fold brightening. So you're going to go from roughly the luminosity of the sun to maybe 100 times the luminosity of the sun, not 100,000 as in a classical nova. And again, this is a gravity-powered effect. SS Cygni is the brightest of all the dwarf novae. It's about 100 parsecs away, so pretty close. And most of the time, it spends its time at around 1/10 the luminosity of the sun. But about every 40, 50, 60, 70 days, it goes boom, pop, and it jumps from 12th magnitude to 8th magnitude and becomes about 10 times the luminosity of the sun. And that's an accretion. That's the white dwarf, that's the accretion disk collapsing onto the white dwarf. The vast majority of astrophysicists, okay, I mean, I love our colleagues, and by the way, they can nail me in the corner. They ask me anything more than cosmology 101. At 202, you got me nailed in the corner. But the vast majority of our cosmology colleagues haven't a clue about the difference between a dwarf nova and a nova, okay? They will not be able to tell you. I've just found this. So you all now are responsible to know the difference. If you go on to great careers in cosmology, God bless you. But a dwarf nova is an accretion brightening 10-fold, 100-fold, okay? And it's a sneeze, okay? Whereas a classical nova is full-fledged pneumonia, okay? And you need 1,000 to 10,000 dwarf nova events to accrete enough hydrogen onto a white dwarf to get the thermonuclear runaway that makes a classical nova.
It's going to add that that's true for also most extragalactic supernova. It's the difference between a dwarf nova and a classical nova.
Thank you. Thank you for making it's not just me, right? Okay, we know it. Yes.
So will all classical nova be preceded by many dwarf nova?
Excellent question. And I'm going to spend a bit of time talking about that now. The answer is basically yes, except for some cases.
So what's generating the periodicity there?
Oh, in the dwarf novae?
Yeah.
It's not periodic. So you can never predict, nobody's been able to predict with precision when the next dwarf nova event is going to be. There's a range. So in SS
So
Cygni,
it just kind of like the shutting on, the on and off of the accretion.
that's correct, builds you up to a critical level, okay, a critical mass, hence a critical density in the accretion disk. So this instability happens. But you don't, the thing is, you don't empty out the accretion disk each time. So the starting conditions, the initial conditions to building that disk are slightly different from eruption to eruption. And the white dwarf temperature goes up and down, and you feed back onto the red dwarf. So you've got at least 3 knobs that you can twist. And that's why it's not a perfectly periodic system. It's roughly periodic. And I don't want to go into the details of it because the study of the eruptions of dwarf novae, I mean, no 2 hiccups are the same, no 2 raindrops are the same, no 2 dwarf nova eruptions are the same. There's always slight variations between one another, again, because there's at least 3 parameters in the binary system. So before 1986, white dwarf binaries were looked on as the following sorts of systems. Novae, which reach 10 to the 5 solar luminosities, up to 10 to the 6. And if you wait 10, 20, 30, 50 years later, you then see them become systems with 1 solar luminosity of brightness, and they are main sequence stars, GKM dwarfs, transferring matter onto a white dwarf at rates of 10⁻⁷ to 10⁻⁸ solar masses a year. Okay, that was one class of these things, hard line between them. And then there were the dwarf novae with luminosities of 1/10 the sun to 10 times the sun when they go into eruption. Same kind of system, always a white dwarf and a red dwarf, white dwarf, red dwarf. But the mass transfer rates were 10 to 1,000 times lower, 10 minus 9 to 10 minus 12 solar masses. Okay. And of course, there are detached systems, detached white dwarf, red dwarf binaries, where the mass transfer rate is immeasurably small. And those were believed to be three separate animals. Okay, those were lions, tigers, and cheetahs. They had nothing to do with each other. Maybe some kind of, who knows, distant common ancestor, but that was the picture before 1986. And there was enough evidence accumulating that I was lucky enough to be in the right place at the right time, having gone to the right summer schools and listened to the right masters of CVs, to understand that they all have to be the same thing and that there has to be a mechanism that connects them all. So because they have the masses of the white dwarfs that are measured and of the red dwarfs in dwarf novae and classical novae and nova-like binaries are all the same. Okay, it's not that there's slight overlap between them. They are all the same. So they have to be the same system. Okay, I take a puncture of my cheetah and my tiger and my lion. I look at their DNA and it's all the same. Okay, so somebody has maybe changed their spots or put on a different jacket, but something's going on, but they're all fundamentally the same system deep down. Well, the difference is the instantaneous mass transfer rate that you measure. The nova-like variables, the things after a nova, typically 10 minus 7, 10 minus 8 solar masses. Dwarf novae, 10 minus 9 to 10 minus 12 solar masses. That's a big gap. And the detached guys, well, there's just two stars sitting there not doing anything. Why is this true? So that's the paper, the very first paper that we put out. And fundamentally, we said, when you get a nova eruption, the red dwarf in a nova binary will lose contact with its Roche lobe and will stop transferring mass after the eruption and after irradiation from the white dwarf, because you lose mass from the white dwarf. The gravitational pull between the two stars goes down. You've lost a certain amount of mass and angular momentum. Fundamentally, the stars separate. Now, if you lose 10 to the minus 5 solar masses from a system of one solar mass or two solar masses in total, the delta A over A, that is the change in the separation, is roughly twiddle delta M over M. They're the same thing. So about 1 part in 10 to the 5th. And you say, 1 part in 10 to the 5th, I mean, really, who cares? What does it matter? Well, the difference between being in contact and not being in contact is huge. Okay, if you're not in contact, if your red dwarf is no longer in contact with its with its Roche lobe, then mass transfer is going to drop. And it can drop by many orders of magnitude. And your system can go from a cheetah to a tiger to a lion. It can change its appearance dramatically. So that was the postulate, that a nova means you lose mass, the stars separate, mass transfer drops to 0, or to a low value, but not immediately, because while the stars have separated, the hot white dwarf takes a long time to cool off. And the hot white dwarf keeps irradiating its companion. So for a century or a few centuries, it's going to continue to fill its Roche lobe until that heat lamp shining on it drops from thousands to hundreds to tens to single digits solar luminosity, at which point the star can finally relax and stop transferring mass. That's the fundamental idea of the so-called hibernation scenario. And the quantification of the white dwarf cooling timescale was an important problem that we didn't solve in that first paper. It turns out to be a few centuries, not surprisingly, but anyway, that's the answer. So it's an unfortunate number in a sense, because most of us aren't going to live a few centuries. You might. I mean, most of you are young enough. It's possible. I am unlikely to. And so I was safe, okay, in making this prediction. because I won't be around to see the outcome in most cases. But anyway, there's our prediction. So the post-nova white dwarf cools for about 500 years. And during that time, the irradiation of its companion decreases. And so the companion, which is forced to remain in contact with its Roche-Lobe because of the heating of the still hot white dwarf, is always going to look like a nova-like binary, high mass transfer rate binary after a nova eruption. But centuries later, it can fade away. And in particular, as the mass transfer rate starts to drop, it can go from nova-like binary to dwarf nova. So the answer to the question is, right, you're not going to be a dwarf nova right away, but you are going to become a dwarf nova, okay, after some number of centuries, maybe as small as 1 century, depending on the mass ratio, separation, all this sort of stuff.
Like, does that mean you wouldn't ever expect the recurrent novae with the really massive white dwarfs to hibernate?
To what?
To hibernate, because the cooling time scale is longer than the recurrence rate.
Right. So in the case of the recurrent nova, which I'll come to in a little while, you have very massive white dwarfs. You have white dwarfs typically of 1.3, 1.35, 1.38 solar masses. And you have high mass transfer rates onto them, either because you're in a red giant, either because you have a red giant or because you have a subgiant transferring mass onto the white dwarf. That's the cause of most recurrent novae. And the fact that you have such a massive white dwarf means that you only need a thin envelope, not a Pacific Ocean. You only need a Hudson River's worth. You only need 10 or 20 meters of hydrogen on top of a very, very massive white dwarf, an England-sized white dwarf, not an Earth-sized white dwarf. That is 1.37, 1.38 solar masses. So the recurrence can be very rapid because, you know, you can put the 10⁻⁷ solar masses needed, not 10⁻⁵, you can get 10⁻⁷ on in just a century or just a decade. Case of one nova and Andromeda, in just 1 year, you can manage to get it onto the surface of the white dwarf. But I don't think I answered. I don't think I.
I mean, you did at the beginning.
Okay. All right. So the idea then is that you get a nova. A nova goes off in a system like this, which is transferring mass onto the white dwarf. You blow off mass. You continue to shine on the red dwarf. You keep the red dwarf filling its Roche-Lobe until this guy cools down, at which point you move over to this. Okay, so you move over to a detached system, and that, in some sense, explains the vast diversity, because the transition from here to here also includes the dwarf nova step where the mass transfer rate is going down. So you expect the mass transfer rate between the red dwarf and the white dwarf to not be constant over many centuries. You expect it to vary. Now, once you've separated, why would you ever come back again? Well, because there are angular momentum losses from the system. As you as a star plow through space-time, you're going to be generating gravitational radiation. So that sets a minimum rate at which you lose angular momentum from any binary system. You also lose angular momentum because the red dwarf, when separated, has a wind. The sun has a wind. All red dwarfs have winds. The winds carry away angular momentum from the system, and so the combination of the two is going to bring the stars back together again. And so you go back and forth, back and forth, back and forth, tens of thousands of times over time scale of giga years to make a nova, which becomes a nova-like binary, which becomes a dwarf nova, which becomes a deeply hibernating separated system, which is then pushed back together by angular momentum losses, back and forth, back and forth, back and forth. So that was the sort of semi-quantitative hand-waving picture that we had back in the 80s, 90s and the aughts, just because we didn't have the computational capabilities to do much. So let me, and that's now changed. So I'm going to describe the more sophisticated set of simulations that we have today and ideas that we have today. But let me first talk about three predictions that come out of this very, very broad basic picture of the hibernation scenario of the evolution of cataclysmic binaries. The first is that old novae fade. As the white dwarf cools down and the mass transfer rate from the secondary star to the white dwarf goes down, old novae should get fainter by factors of anywhere between 2 and 100 on a time scale of centuries. That's number one. Number two, that the nova-like post-novae with very high mass transfer rates will eventually flip over to become dwarf novae as the mass transfer rate drops. At very high mass transfer rates, you don't get the disk instability. At lower mass transfer rates, you do. And you will eventually get metamorphosis. That is, you will go from a nova-like to a dwarf nova, just like an egg, chrysalis, caterpillar, and butterfly are the same system. They look wildly different. You will get metamorphosis between these different kinds of CVs, and they will cycle back and forth between each other. And finally, still the most controversial of all the predictions is that there is, for most CVs, a period of deep, deep hibernation between nova eruptions. Most of the nova-like and dwarf nova systems that we see in the sky, or the numbers that we see and the densities of objects we see, are only the tip of the iceberg. The vast majority are actually separated systems. So how do we test this? Maybe we should take 5 minutes. I see a few people getting fidgety. What do you think? Show of hands. Who would like to take 5-10 minutes? Nobody. All right. If you want to go, you can go. Okay, bathroom's right around the corner. All right. Do novae fade? So the first question is, do novae fade? Well, you need novae that are at least a century old, and you need records of them. Happily, the American Association of Variable Star Observers, God bless them, I love these guys, have been observing many novae for many years. So B603 Aquila, nova of, I think, 1903 or something like that, has been followed for a century, and it is decreasing. Now it wiggles and waggles. All CVs wiggle and waggle, if for no reason other than the fact that their red dwarf companions have magnetic cycles, okay? And the magnetic cycles have to have an effect on not just the Roche lobe filling, but if you plant a large magnetic spot near the pointy place of the Roche lobe, you're going to knock the mass transfer rate down or up by factors of 2. So we expect this sort of thing, but the long-term evolution over a century is downwards. In the case of DK Lacerta, I think it was Nova 1920, it stayed pretty constant for the better part of a century, and now it's definitely on the decline. So we don't see systems getting brighter. We only see them either constant or going down. Question.
This might be too much of an aside. I'm just curious about archival observations going back pre-digital cameras. It seems like there's 2 populations of data points for the top nova, where there's a very higher confidence that shows like almost a sub-periodicity, and then a less confident kind of scatter shot. And I'm just curious, when you're trying to pull data out from that long ago, how you actually get good photometry.
The only way of doing it is from these wonderful things called photographic plates. I'm sure many of you have either never seen one or never handled one, but as obsolete as the slide rule. Nevertheless, it's the only record we have going back a century in astronomy. And you probably know about DASH, the digital archive at Harvard. It's a magnificent accomplishment led by Josh Grindley, where 1 million photographic plates have all been digitized. So you can check things like this. The answer is the plates are the collections of plates are very heterogeneous, different focal lengths, different telescopes, different emulsions, and it took decades to get enough photometric standards across the sky to be able to calibrate all of these things. So I think that part of it, some of the scatter, not all of it, but some of the scatter is due to the fact that you have such heterogeneous plate collections. So some of these are taken by European observatories, okay? Different, again, wildly different plates, plate scales. There was nothing standard. But in the end, if you're really interested, you need to go back and look at the data, look who did it. Was it done by eye or was it done from these digitized plates to give you an idea of what's going on? In the case of these two objects, I don't think there's any doubt that that's the very long-term trend. The wiggles and waggles aren't well understood. It's as simple as that. So generally 100 years of decreasing mass transfer rate isn't enough to get you from the old nova state, the nova-like state, to the dwarf nova state. But 500 years is enough time. So I'll tell you a little amusing story now about how you find a 500-year-old post-nova, okay? Nobody was taking photographic plates at all 500 years ago, or 300 years ago, or 200 years ago. But there were lots of Chinese, Japanese, and Korean imperial astrologers. Okay, the stars obviously told the future, the fortunes of mankind. It was so obvious that you didn't even need to state it. And the stars weren't interested in you or me, but they were interested in the kings and queens. Okay, who paid the salaries of the astrologers. And so there are 2,000 years of fantastic records in China, Korea, and Japan of transients. I mean, not just of transients. In these imperial records, everything the king or queen did on this day. Okay, he had 2 eggs for breakfast, or there's one great case. He fell off his horse and broke his leg, which was scrubbed. It was hidden for 50 years because he would do something stupid like that, but he did. Anyway, Korean astronomers tell us that there was a transient on the 11th of March, 1437, which had to have been very close to 0th magnitude. And it happened in Scorpius. So the Sejong Salok tells us exactly what happened to King Sejong almost minute by minute through his lifetime. It was written in classical Chinese, and chapter 76 states, 19th year, King Sejong, second lunar cycle, Day Yi Chao. A guest star began to be seen between the 2nd and 3rd stars of Wei, nearer to the 3rd star, lasted for 14 days. So it was between this star and closer to this star. That almost never happens. Usually there's a transient in the east, okay, or something like that, useless. But here they told us exactly where it was, and it lasted for 14 days, and that's too fast to be a supernova. Okay, but they saw it on every one of those 14 days. We're getting a little fainter, little fainter, little fainter, little fainter. So it wasn't a comet either. Okay, that's really rare. There are only half a dozen such events throughout history. And Wei is in the tail of Scorpius. The 6 stars, this is the 6th lodge of the moon. The lunar princess, as she moves around the celestial sphere, takes 1 month, okay, to move around the celestial sphere, moves through various mansions. Princesses don't live in huts or hovels, they live in mansions. Each of the mansions is a constellation on the sky, well documented by historians of Chinese, Korean, and Japanese astronomy. And so the nova had to be between these 2 stars. Okay, and that's spectacularly well located for an ancient transient. And I spent 20 years looking for the damn thing and couldn't find it. Bastard. Drove me mad. Part of the problem is there are 10 million stars brighter than 20th magnitude is in Scorpius. Okay, it's like in the worst part of the galaxy. You just couldn't pick a worse place to put a nova if you wanted to find a nova. And not one of them is an old nova. There's nobody there. Just empty. So finally, I had a light bulb moment. I mean, not I read a lot of this stuff. It turns out that how do you order the stars? Which is star number 1, number 2, number 3, number 4? By the way, this is the constellation Scorpius, okay? Which really does look, at least to me, like a scorpion. It's one of the few constellations on the sky. You look at it, damn, that's a scorpion. Okay, it works. The Big Dipper, the Big Bear, give me a break. Oh, the Dipper. Okay, it kind of looks like a dipper, but a bear. Come on, come on. Okay. The lunar mansion way is here. So the Asian astronomers separated this mansion from that one. They didn't see it as a scorpion. Whenever I argue against astrology, this is one of the arguments that I use. There's nothing universal about any of the constellations, all nonsense. So it turns out that because of the Earth's precession, okay, so the Earth precesses 23,000 or whatever it is years, the order of stars changed. That is, the star that was northernmost, this was to the north or that was to the north, just flipped over just a little bit. So the second and third stars can equally well be interpreted as not just between mu and zeta, but between eta and zeta. Okay. As soon as I did that, you get one source that is recently cataloged as both an X-ray source and ultraviolet bright and surrounded by a beautiful hydrogen shell. There it is. Okay. The star, that's the CV, that's the cataclysmic variable. It's moving in this direction. It's leaving a wake, a little bit of a wake behind it. It's moving right through the galactic plane. And, but you know, there are nova shells, there are shells everywhere. How do you age date this? How do you prove that this is the transient of 1437? Well, the answer is this. So here's the nova in 2016, and you know, you don't need to do precise astrometry to see it's way the hell off center. Okay, and it's moving in this direction. So you can trace backwards, you can trace it backwards, okay, because we have a proper motion. And we have a proper motion because we have photographic plates of it that go back to about 1918 or 1920. The kind of crappy plates, and the thing is sort of diffuse, but you see it's moved a couple of diameters. So we really know what its proper motion is. And we know it better than Gaia. The Gaia proper motion isn't very good, and that's normal for binary stars. So when we trace the proper motion backwards, it ends up right there, right in this. In 1437, okay, or you know, 14 to 1500, something like that. So the proper motion is the clock. You can run the clock backwards and see that it's right at the center in 1437. So that's cool. So we almost certainly have the nova of 1437 based on its shell and its proper motion. But here's the other cool thing. Because we have a century-long record of it, we can look back to 1942, April 1942, and it's barely visible. On the 18th of May, it's a lot brighter. On the 6th of June, it's way brighter, like 3 magnitudes brighter. And then by the 9th of June, it's back to 1942, and this is its normal quiescent brightness. In other words, it underwent a dwarf nova eruption. So this is an old nova that has a 500-year-old nova that has undergone a dwarf nova eruption. So if you need proof that these systems change their mass transfer rates to go from high mass transfer rate old novae to low mass transfer rate dwarf novae, this is the best piece of proof that we have, the best piece of evidence that we have. So we have this stellar metamorphosis. where you had a nova, which has now become a dwarf nova and is heading towards being a hibernating system, a lower mass transfer rate system, which will eventually accumulate enough of an envelope on itself that it will undergo another classical nova, then become a post-nova and continue the cycle over and over. Okay, I told you before that we now think we have a better understanding, and the reason we have a better understanding of the long-term evolution of cataclysmic binaries is because we have so much more computing power than we had back in the 1980s. We can now say, okay, let's take a white dwarf, a red dwarf, and let's allow for a full evolution of each one together with full feedback between the two systems. In particular, I can allow for the post-nova irradiation to increase the mass transfer rate. I can allow for that increased mass transfer rate to accumulate matter faster and faster on the white dwarf. I can calculate the separation during the nova event. I can calculate the angular momentum losses due to gravity in a wind. We can put all of that self-consistently in, and we can do one nova, 2, 3, 4, 5, 100,000 nova eruptions. Each nova eruption, 1,000 shells, following 1,000 shells on top of the white dwarf. All the reactions, every nuclear reaction, follow the dynamical ejection of every envelope. In other words, completely self-consistently follow both stars in the binary for 10 gigayears. And that takes typically 2 years of wall clock time on about the fastest CPU you can find, but you only need one to do one system or two to follow the two stars. And of course, you don't want to do that for just one system. You want to do it for 100 binary systems, because we want to replace that paper from 2005, the Iran paper, because that paper assumed constant mass transfer rate. That was core, that was key. We simply assumed that you have one solar mass white dwarf accreting at 10 to the minus 8 solar masses per year. Well, that's not true. We know that from the Nova 1437 and lots of other things, that the mass transfer rate is varying. So here's the first one we succeeded in doing. We were able to not just model, but follow year by year, completely self-consistently, the variable mass transfer rate, accretion, heating, diffusion, mass loss effects, the whole shebang. This is the recipe that we laid out. And what we found, this is something we had never really properly understood till we did the simulations, was that you have two pathways, not one. Once you get a nova eruption, you always become a nova-like binary because the white dwarf is shining on the red dwarf. You continue high mass transfer rate. And then 10% of the recent novae, 10% become eventually detached binaries. So this is, it turns out, 90% of all novae, but 10% of recent novae. What? How can that be? I'll explain to you. And conversely, 10% of all novae, but 90% of recent novae go into the dwarf nova state, which then go back here. So what we're saying is that 90% of all cataclysmic binaries live here as detached binaries, okay? Takes a while to get here. But all of the novae that we see, 90 or 95% of the recent novae, go from nova-like binary a few centuries later to dwarf novae, never drop down, never become detached systems, and then these become novae. So what's going on? Here is the key diagram that explains, and if you only take one thing away from this lecture, I hope you remember and understand this one slide. We start with a red dwarf of 0.7 solar masses. Okay, that's the very top blue curve. Okay, there's two curves that are almost blended at the top. Can you see them both? Okay. So there's that blue curve. This is a red dwarf of 0.7 solar masses sitting next to a 1 solar mass white dwarf. Very typical nova system. And we get an eruption, another eruption, another eruption. After 1,000 eruptions, okay, cycle number 1050, we've gone from the blue curve to the orange curve. After 8,000 eruptions, we've gone to the yellow curve. After 12,000 eruptions to the purple curve. And then things start getting interesting, the green, the blue, and finally this deep curve. What are they? This is mass transfer rate as a function of time between the nova eruptions. Okay? And this is the only set of self-consistent calculations that have yet been published, where again, the white dwarf, the red dwarf, and all the effects, all the feedback effects between the two are followed step by step by step by step. Thousands of time steps between the eruption, tens of thousands of time steps during the eruption. So we have completely self-consistent feedback. And the lesson to take away is, in no case is the mass transfer rate constant. Okay, here's the nova, here's the next nova. Okay, this is the time between the novae. The mass transfer rates continuously vary. That's the single most important point. And that explains why you see this zoo full of lions and tigers and cheetahs. They're all the same system, but you're catching them at different points along this x-axis between the last nova eruption and the next nova eruption. The mass transfer rate is varying continuously. Now, when you have a massive red dwarf, let's say 0.7 or 0.6, or even down to 0.36 solar masses, the mass transfer rate doesn't change vastly. It changes by about an order of magnitude over the course of the history of the system. And it never gets really low. 10 to the minus 9 solar masses is not very low. That's sort of nova-like territory. Takes a long time even to get down to dwarf nova territory at 10 to the minus 10 solar masses. And to get down to deep hibernation, it's only for these very low mass systems under 0.3 of a solar mass. So if your donor is massive, 0.7, 0.8 solar masses, 0.6, 0.5 solar masses, you're not going to have deep hibernation. You're going to have only a modest change in the brightness. And after a few centuries, you might get down to becoming a dwarf nova, like the nova of 1437. These systems, on the other hand, which drop down to 10 minus 12, 13, 14 solar masses, remain deeply hibernating for 10 to the 5 to 10 to the 6 years, a million years. So here's, say, 10 to the 5 years up to here. These systems are invisible. You will not see them. And because they are transferring mass at such a low rate, when they do transfer mass, they do so at a reasonable number, say back up at 10 minus 10 solar masses, only for a modest fraction, maybe 10% of their lifetimes. So you have deeply, deeply hibernating systems hiding. Again, that emerges completely self-consistently. We postulated something like it, but we didn't understand the fine details 30 years ago. But now we think we do understand that hibernation emerges organically from these self-consistent simulations. And when we look in any 100-year period, why 100 years? Because that's how long astronomers have been observing with tools powerful enough to measure precisely the positions of novae and go back and look what they look like for 100 years. The vast majority of them are the ones that erupt frequently, the ones with a high mass transfer rate. And these are the ones that erupt every 10,000 years. So there's a strong selection effect, a nasty, pernicious selection effect that biases you against detecting those systems that hibernate, because they hibernate for vast periods of time. They are the vast majority of systems. You think they're just boring white dwarf, red dwarf, not connected binaries, and we now have a nice rich catalog of them from Gaia. Okay, but these guys are at least 90% of all the cataclysmic binaries. They're just in deep hibernation. And they only erupt once every million years or so. So the final untested prediction is that these dwarf novae go into deep hibernation. So how do we find them? How am I going to find one of these bastards? The bane of my life. Okay, I need to find a red dwarf, white dwarf binary, and I'll forgive any one of you who does it before me. It's fine. Okay, I need a white dwarf, red dwarf binary that is detached and that has a nova shell around it. Okay. It exists. It must exist. Okay. There's something like 50 or 100 novae that go off in the Milky Way every year. We detect 10, 20, 30 of them. Kishale will eventually find all of them, right? It would be hardware place to find every one of the damn things. Okay, but even if you only find 10 or 20 a year, that means there's 1,000 over the past century. At least 10 of them should be these systems. They're somewhere on the sky. Okay, and that will be the, you can never prove anything in astrophysics, you only prove the things are false. But that will be the single most important piece of evidence that connects all kinds of cataclysmic binaries into the hibernation picture. All right, let me go on to another topic. I want to talk about novae in the Virgo cluster of galaxies. I've already kind of expired my time. Can I take another 15 minutes? All right. Yes, no choice.
Jenna isn't lecturing, so let Mike take some of that time. Or you will have a 30-minute coffee break.
I'll try and keep it to 10 minutes, all right? So I've been looking for many, many years with the Hubble telescope at M87, trying to find the novae going off there. I have a couple of unique data sets. I have 72 days, boom, 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 picture of M87 every day for 72 days. And then 270 days of every 5-day images in the ultraviolet also. And the goal was to measure the rate of novae in a giant elliptical galaxy and in a giant spiral galaxy to look for supernova progenitors, to see what the rates of novae in galaxies are, and so on. So here's M87. Here's 135 novae that we have detected around M87. I probably don't have to work too hard to convince you that they are concentrated towards the center. Novae follow the light of galaxies. Where most of the light is where most of the mass is where most of the novae are. Schiffer-Mandel at Columbia took a long data set of M51 images. We were only able to get partial coverage of the galaxy. M51 is bigger on the sky, but nevertheless, she found a sample of novae there. Here are two of the light curves one light curve in M87. This is in ultraviolet light, and you see the nova peaks. So here's day 1, 2, 3, 4, 5. Day 1, 2, 3, 4, 5, and you see that the ultraviolet and visible light curves are not the same. Novae reach maximum brightness, typically in visible light first, in ultraviolet light later. We have light curves in the V band, the I band, the infrared band. Novae are extremely blue at maximum light. They are reddest at maximum light, but they're still very blue. B minus V is typically 0. Afterwards, they become very, very blue. The reason is that as you blow off the envelope of a white dwarf, and you can see deeper and deeper, you see into hotter and hotter regions, so that these systems become bluer and bluer. We're able to determine, because we have so many novae and such dense time coverage, that the nova rates in M87 and M51 are about 363. So there's a nova a day in M87, called the vitamin galaxy, take one a day. And in M51, there's 154 novae, a nova every second day in M51. And all of the previous reporting in the past were rates that were 3 to 4 times lower. So are M87 and M51 unique? And the answer is, of course not. All the previous ground-based surveys were about 75%. They missed 2/3 to 3/4 of all novae. And that's because astronomers don't want to believe that their data are less than perfect. They're not, okay? Surface brightness effects kill you in the centers of galaxies, and only Hubble is basically immune to these problems. The other thing is when you get ground-based telescope time allocation, until recently, and this has been the bane of everyone who loves transients. Everybody who loves transients knows that you need coverage like a clock, okay? Either every day or twice a day or at least once a week, but you need it bang, 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 bang over again. And only Hubble, until recently, has been able to do that because it's immune to clouds, it's immune to weather, it mostly doesn't fail. And so the understanding of what the real rates of novae in galaxies are, which are way up here, this is the luminosity corrected nova rate, okay? The number of novae per year per 10 to the 10, L sun in the K-band. These are the numbers. These are the correct numbers, and these are all the ground-based rates. And all the ground-based rates are wrong because they were wildly incomplete. The crazy thing we found, and that I don't understand, and I put this one out in front of you, is that novae love the jet of M87. Okay, we know that M87, the nearest big giant elliptical galaxy, has a jet. There's a supermassive black hole in the center, which is doing weird stuff and ejecting a jet of plasma at nearly the speed of light there. Okay, so we just count up the number of novae in sectors around M87, and with 99.7% probability, I mean, it could be a dumb, stupid fluke, but you know, it's highly unlikely. There are twice as many novae in this sector as anywhere else. So is the jet somehow irradiating, like is it putting enough luminosity into the binary systems to increase the mass transfer rate so that basically doubling the mass transfer rate? The answer is not even close, okay? You can do the calculation back of an envelope. It doesn't change the mass transfer rate by 1%, let alone by 100%, which is what you would need to explain this. So is it possible that novae are being born here? Maybe this is relevant, or a good fraction of the novae are being born in M87, and that's no. The answer is no. The dynamical time scale is short enough in M87 that even if all of the novae were born here, they'd be mixed around the galaxy fast enough that you wouldn't see any such effect. So we don't know why it's happening. I'm just telling you it's happening. Published it last year. It's, I think, a weird finding. Jets somehow are, the jet in M87 has got an enhanced nova rate around it. Okay.
You don't see any such accumulation around the counterjet.
You don't see any?
Like the reason we don't see the counterjet is because of relativistic beaming. But
Okay.
Novae I wouldn't expect Novae to have such a selection bias, right? Novae aren't relativistic transients.
Correct.
So if the jet is causing it, I would expect to have an overdensity of Novae also where the counterjet is.
It's an excellent point. I hadn't thought of that. Thank you for suggesting that. It's an observed effect.
I mean, maybe it's dust attenuation. That, you can always explain things with dust. But
I think not the novae, because we have the light curves of the novae all over M87, and they're indistinguishable from each other. Whether along the jet And we've checked their light curves, their speed classes, everything about them. There's nothing different about those novae or their reddenings or apparent colors. No difference at all from the novae on the other side or anywhere else around the galaxy. So I think we have solid evidence that it's not dust, whatever else is going on. I don't know what the cause is, but it's not dust. Yes.
Do you have a hunch that this is like some physical cause of this and not some observational bias?
If I knew, if somebody could put on the table, could suggest an observational bias that might cause this, we just heard one, but I know it's, okay, I can discount it because I see that, I observe that the colors of novae are all the same all over the galaxy. If there is some other observational bias that does it, I'd be happy. Okay, I don't have a dog in this particular fight. It doesn't have to be some weird physical reason. If it is just a bias, an observational bias, terrific. That's cool. But if anything, you would think it would be harder to discover novae along the jet because that's the brightest place in the galaxy. And in fact, right along the jet, it's very hard to discover novae. So if anything, there may be more novae that we're missing right inside the jet. Okay. I don't know. I honestly don't know. Symbiotic stars. So I'm stepping over into Geno's territory here. Symbiotic stars are basically red giants with white dwarfs. The white dwarfs are accreting either from the wind of the red giant or from Roche-Lobe overflow or from both of them. And there are two flavors. Either it's a giant or a supergiant. If it's a giant, a normal giant, this is 80% of all symbiotic stars, mass transfer rates are around 10⁻⁷. Orbital periods are a few years. Orbital periods are a few years because the separation is of order in AU, which is the size of the red giant. So the red giant is pretty close, dumping some stuff onto the white dwarf. If it's a supergiant, then it's got to be 10 times bigger. The orbital period's 100 times longer. So then the orbital periods are centuries to millennia. And these are the Myra dusty, and these supergiants emit a lot of dust. So those are the two flavors. These are promising factories for type 1a supernovae. They make novae too. Okay, there are symbiotic novae because there's hydrogen being transferred onto a white dwarf. Doesn't matter where the hydrogen, ultimately where it comes from. And in the case of the recurrent novae, you have these systems with high mass transfer rates and very massive white dwarfs. When you have white dwarfs that approach the Chandrasekhar limit, you no longer need 10⁻⁵ solar masses. You're happy with 10⁻⁶ or -7 solar masses of accretion, which means you can get a nova every 10 years, 20 years, 30 years. In one case, in Andromeda, there's a nova that goes off every year, almost to the dot every year. It's got to be 1.39, like right up against the Chandrasekhar limit. And it's got to be smaller than England. Okay, tiny little white dwarf, super, super high gravitational field. It just accretes a few meters of hydrogen before it floats up. When you do simulations at constant mass transfer rate, you find that once you exceed around 10⁻⁷ solar masses, once you get to say 2 times or 3 or 4 or 5, 6 times 10⁻⁷ solar masses per year, the effective mass accretion rate is such, maybe that you retain 30, 40, 50% of the hydrogen that you accrete. You burn some hydrogen into helium every time. You don't eject the whole envelope, and this can grow your white dwarf towards the Chandrasekhar limit. Here's an object in Andromeda, a ground-based view, a Hubble view. This thing is 120 parsecs across. This is a recurrent nova, which goes off again and again and again and again and again. It snow plows everything up around it to make a giant nova super remnant. Not a supernova remnant, a nova super remnant. And we've been looking with a lovely little telescope called Condor, and we have found 3 more. Here's the shell around T. corona borealis, around RSO Fuyuki, and we just a few weeks ago found the one around V2487 Ophiuchus, which is 200 parsecs across, which is the largest coherent structure of any kind of stellar ejecta known. Okay, so to summarize, what we talked about today were the metamorphosis into dwarf novae and back again of old novae, mass transfer rates varying, prediction that most novae hide, deeply hibernate, and looking at novae in galaxies, the rates are much higher than previously thought. These are strong constraints on binary population synthesis, and the observations are now in much better accord. I didn't emphasize that. Strangest thing that I found is that the novae preferentially erupt along M87's jet. I don't know if it's physical or an observational bias. Open to all ideas. And in recurrent novae, there certainly are type 1a progenitors because you have the combination of very massive dwarfs, massive white dwarfs, and very high mass transfer rates, which retain some of the burnt hydrogen as helium on the surface of the white dwarf, which can push the white dwarf over the Chandrasekhar limit eventually, leading to a type 1a. And they're all surrounded by vast shells. The 4 that we really have good data on, where we've looked faint enough, all of them are surrounded by nova super remnants. Okay, Kishore really wants me out of here. Any final questions?
Thank Mike. Right, any questions?
So how does this picture fit in with like the observed period gap in like CVs? Like do you expect the hibernation time to be longer, like some the orbital gap, or like?
Right. And thank you for bringing that up and giving me the extra minute I needed, because I didn't have time to address it. When you look at the number of CVs as a function of orbital period, you see there's lots of them between about 90 minutes and 2 hours. Then there are very few, or fewer, between 2 and 3 hours, the infamous period gap. It's not exactly 2 and not exactly 3, but never mind. And then the number grows quite rapidly again, peaks at around, maybe 4 hours, and then tails off. And then you get a long period tail distribution. So why the gap? So the orthodox theory has been for many decades that what goes on is that you have your CV, you have your, say, your 8/10 of a solar mass red dwarf and 1 solar mass white dwarf, and you're transferring matter, and the mass of the red dwarf goes down because you're losing mass. And eventually you flip over, when you reach around 0.3 solar masses, you reach over, you flip between a radiative and convective star, fundamentally. Okay, and that when you do that, the star shrinks enough that between 3 hours and 2 hours, during that time it's losing angular momentum, there's very little mass transfer. It becomes basically a detached system. Okay, now if that was all there was, that was the whole story, then you would see no systems in the gap, but there are systems. And what used to be a gap is now really a dip. Okay, so observations have shown that the gap is not only not absolute, it's, a factor of 2-ish or 3-ish down, something like that. So one explanation is that systems are born into the gap. So you actually have a 0.25 solar mass red dwarf or a 0.3 solar mass red dwarf that is losing angular momentum with its companion, is not touching its Roche lobe, and then because of loss of angular momentum, at some point, boom, it actually does fill its Roche lobe while it's 0.25 solar masses and starts transferring matter there. So that's an explanation for some systems in the gap. Hibernation, I think, can fill in a lot of that gap too. When we do our self-consistent simulations, we find systems that go, that are in the gap that don't much care about the gap. Now, the idea that stars change their structures dramatically when they reach the top, near the top of the gap, near the 3 hours, and are very different stars, that is fully convective stars when they come into this, that's true. There's just no question about it. And that's got to be part of the explanation for the gap. But for the dip, I don't use the term gap anymore, okay? But I don't think it's the whole explanation. Anyway, it remains an active topic of conversation with strong adherence on each side of the argument. At all CV meetings, it's an unsolved problem. Thank you for bringing it up.
Okay, I think we should head over to coffee. Let's thank Mike again.
So we are in our last session, the last lecture session. We still have the afternoon module on, so please come back for that. We'll see about how to do search for interesting periods in time series like LSST. So this session will be all about you instead of lecturers lecturing you about things. We want to hear about what research you've been doing, what you're most excited about with LSST, and especially if you've learned anything useful from this book. So the way we try to do this is that you all uploaded slides. Last I counted, there were 25 of us. And the way we would do this is that we have about 75 minutes of time. And so there are 25 slides. We'll try to stick to 3 minutes per slide. So what I would recommend is that you come up here, you speak for exactly 2 minutes, and then leave 1 minute for any burning questions and transitions, so that we can stick to 3 minutes per person. And I will be moderating this session by rolling through the slides. So I do have, just to make sure we're all on time, I do have a timer set on my phone. So if you go over time, you will hear this. So I will set the timer to 2 minutes for all of your presentations, so that we have time to do transitions. Okay. Right. So I haven't really bothered to change the ordering of things. So whatever the slide order was, we'll just stick with that. So let's see. So yes, just come up here. The microphone is on. Speak. Yeah, try to get other people excited about what you're doing.
Do we have to come up? Like,
Yes, you have to come.
Like, make sure that you have your face. You also see the rest of you.
Is walking the podium part of my 2 minutes?
Was that? No, that's the 1 minute for transition. Okay. Hopefully you can. Yes. You can sprint. Let's see. Okay. Who's on first speaker?
Oh, I'm first.
Oh.
Sorry. It's like too far away. You are done. Oh my God, there's like an
No.
Oh, that's sorry.
Okay. All set. Go.
Hello, everybody. I'm Sam. I'm so excited to be here. It's been a great school. Thank you, Kishalai. I've learned a lot about a whole bunch of different classes of transients. I am at Caltech, where I work in the CCA Transient Facility Collaboration. So I spend a lot of my time classifying supernova for various surveys. The survey that is nearest and dearest to my heart is the Red Astronomical Transient Survey, also known as the RAT survey. You guys like them? So this is a systematic near-infrared study of supernova discovered by ZTF. It's a flux-limited survey brighter than about 18.5. And it sort of has 3 components. So ZTF is the discovery engine for this survey. And then I do follow up with mostly with the Winter telescope, which is another telescope on Palomar. It gets J, YJ, and H imaging of various of these objects, and I look for infrared excesses as signatures of dust formation or pre-existing dust around the supernova. I also do follow up with Tech2 diagrams when it isn't fucking broken for fucking months at a time. And when it's working, I get spectroscopy with DIRAs and look for signatures of deformation, including emission from carbon monoxide. I'm also interested in these gap transients that we heard a little bit about yesterday, these giant stellar eruptions and LBV stars, the luminous red nova, which might also form significant amounts of dust. So we have a JWST proposal for a survey proposal, which means you get some fraction of targets to do mid-infrared imaging with Ryan Lau and Jacob Jensen, who are both at IPAC, also with Barrage, and look for signatures of dust formation in these lower luminosity transients. Yeah. Okay.
Time. Any burning questions? I mean, this is just to encourage you all to talk to Sam after, whenever. Yeah. Either here or somewhere in the future. But okay. So let's stay on track. Who's next? Andrew. Yes.
Hi, everyone. So that's what I look like in the top left. And yeah, so regarding my research, I think Brian did a lot of heavy lifting for my most recent work on magnetar giant flares as our process sources. So just to recap, we basically did some calculations, nuclear reaction network calculations to predict what our process elements are produced. Then we calculate the gamma ray signal, and our model essentially matches the data from the last galactic giant flare basically perfectly. The light curve, total energy budget, gamma ray spectrum. So this basically confirms that magnetar giant flares are the second confirmed source of heavy elements in our universe. There is, aside from the gamma ray signal, there should be an optical UV thing, mini kilonova-like thing, also an infrared, but probably peaking in optical UV. We expect this to peak at 10-15 minutes, which is quite short. For the 2004 event, this would have peaked at like 4th magnitude, so naked eye, but it was behind a lot of dust. It was near the sun, so probably couldn't see it. But if anyone's interested in figuring out how to detect this, get in contact with me. Kind of what I'm working on now is, if these, we know these flares produce heavy elements, so as this material is ejected, you should get a reverse shock, kind of what Rand talked about, the deceleration time, and this reverse shock will accelerate heavy nuclei to cosmic rays. So we're basically calculating the cosmic ray flux from these magnetar flares, in particular the heavy cosmic rays from these events. So that's kind of what I'm thinking about right now. Previously, something that's more connected to LSST is the effects of our process in hydrogen-rich core collapse supernovae. So I talked a little bit about this, but it's kind of an open question of whether supernovae can produce our process. We basically found that in order for this to be observable, you need to produce at least 10⁻²⁴ solar masses, and it's going to have some peculiar effects on the light curve. So if these things exist, then our prediction is that LSST should observe 100 to 1,000 of them. So keep an eye out. Yep.
How bright are the things on the left?
For a 5 megaparsec source, about like -20. So Argus can probably, actually no, Argus would be able to see galactic source, but I'm not sure.
Hi everyone, I'm Rafael. I'm a grad student at UVA, also working at NRAO, and I work on multi-wavelength autopsies of CSM interacting supernovae. So right as we've heard a few times during this school now, a lot of massive stars lose large amounts of mass before they die, and then when they explode, the ejecta can catch up to that circumstellar material and create multi-wavelength emission through the shocks that form. So I use radio, optical, and X-ray telescopes, so BLA and GMRT, LBT, Magellan, etc., as well as Chandra and Swift, to try to understand the full mass loss history, because basically, right, the ejecta is much faster than the CSM, so as time goes on, you see this material that was lost longer and longer before the explosion. So basically trying to understand the full mass loss history, and through that, understand what kind of progenitors can create these CSM interacting objects. So most of these are type 2Ns, but I also work on 1BNs. Triple envelope supernovae also interact with their CSM sometimes, so also those. And basically trying to figure out by observing in all wavelengths where they emit, whether we can really construct the picture with the shock speed, the CSM speed, and all the relevant variables to fully accurately model the mass loss history of these objects and put them into these plot. Whereas you can see almost all objects don't fall into single star models because we think a lot of these come from binary systems or LBB eruptions. I'm excited for LSST to look at rebrightings that could suggest CSM interaction in a lot of objects, or to see whether some old 2Ns are still around, but we just haven't reached them because of the limiting depth of previous surveys. So yeah, that's me.
It's probably the case that in the LSST era, become quite difficult to follow up, do multi-variant follow up for all things of interest.
Yeah, sure.
So is there like a vision for a strategy for how that might work?
I think we're sort of thinking about that right now in the radio, like how we'll select targets and stuff like that, right? Because yeah, in the radio you're just way more limited in what you can follow up. It's very complicated to get these interferometries to get on the source at all. Interferometers, I mean. But yeah, I think that the unfortunate thing with the X-rays is right, Swift is going away. So that would have been the ideal thing, that Swift could just follow up a lot of these things. But without that, it's not clear. In the radio, though, we have PMRT programs that are set up to observe at least like 40 to 50 supernovae a year. So we can probably try to get a fair amount of those that we're getting from LSST. But yeah.
Hello, everyone. My name is Brian. I am a grad student at University of Arizona. I'm part of the Transient team that follows on a lot of interesting objects as part of the collaboration at DLT40 and also at Los Cumbres, the Global Supernova Project. I use mostly optical and near infrared instruments, and my goal is to use both photometric and spectroscopic observations to infer the late stage evolutions of the massive stars, such as red supergiants and LBVs, all kind of stuff. Mostly I'm interested in using very early time flash spectroscopy, where you see narrow lines indicative of interaction between the star and its CSM environment, and also using nebular spectra to sort of reconstruct the chemical profiles and also the geometry of their progenitor stars. I'm also interested in the host environments of these transients and a lot of other things from dust formation to spectral polarimetry. Questions?
Hi, everyone. My name is Emily McPike. I'm a master's student at the CUNY Graduate Center and at AMNH. And my project for my master's thesis is trying to simulate the light curves of flares. If you guys remember the exercise we did a few days ago, the proposed AGN channel is you could have embedded binary black holes, stellar mass binary black holes in AGN disks. And we think, based on LBK measurements of overly massive remnant black holes, that this is a real channel. It's not a crackpot theory. And one of the benefits of modeling mergers in the AGN channel is, of the 3 LBK channels, you have the isolated binary channel, the globular cluster channel, the AGN channel. The AGN channel is the only environment in which you are always merging, surrounded by a gas supply for you to accrete onto yourself and possibly have some type of interaction between you and your environment such that you produce some type of counterpart electromagnetically. And these can be used, if they are in theory detectable at all, as standard sirens. So these are very beneficial to cosmology. Thus, it benefits us to model these flares. What do they look like? when would we expect to see them post GW detection? How often would we be able to observe them? It would take an incredibly powerful event to actually overcome the bulk luminosity of an AGN. So you need some type of powerful either like GRB jet or any type of other strongly energetic phenomenon or otherwise. And another thing we are trying to find is which AGN are we likely to most find them in, or like have them be most detectable? Is there some type of bias, like how do the host properties like of the AGN impact detectability? And so that's it. That's me. Any questions? Thank you, guys.
Hey everyone, I'm David. I'm at UW working with Eric Bellum. So here are two things I'm doing. No, that's fine. They're transitions. So there are two things I do. One is I look for low mass X-ray binaries in the CCA alert stream. So it seems like the outbursts discovered in the optical tend to be very X-ray faint. So we might be missing some light class of outbursts or biased towards at least the ones that are X-ray bright. You know, that's why they're called X-ray binaries. And so we do things like look for in the light curves for these like basically opposite of FOS. So there's like red, extincted, slow, like transients in the plane. And then, you know, I follow them up. And so this one in particular is a Novae, very strong emission wise. Turns out there aren't very many X-ray binary outbursts. So this might be like the most interesting thing I've found. And again, this is kind of the full light curve. And then I also work on LSST alert production and thinking about how to like leverage LSST in conjunction with other surveys. So recently I wrote a paper on like cross-matching the DP1 data set to all like X-ray source catalogs. Turns out the fields in DP1 that are best observed are all extragalactic. So most of these are AGN. So that's like known AGN and sort of where they fall in X-ray and optical space versus all matches. And then some flux ratio color plots. So I don't really do extragalactic transients. So if anybody has any ideas on what to do with this data set, I would love to hear about it. But you can also talk to me about alert production in general, galactic accreting transients, or like early LSST data. Okay, sorry, I don't know what I just did. Oh, there we go. So yes.
Yes.
I should just read your paper, but if I remember correctly, in BP1, they also observed some fields in the Milky Way, like the Seagull Nebula. I was wondering if there were any alerts that were cross-matched to the X-ray catalogs from there. Or...
Yeah, so there are no alerts in BP1, but there were some sources, and I didn't actually use the Seagull Nebula because I think that was like a test of like nebulosity in that field. So I don't know how like well the pipeline works. In fact, there are a couple of galactic fields, including like, and there are like, those are very sparsely observed by X-ray. So there are a couple, like maybe on order of tens of matches. So yeah, we could talk about those with like, thanks.
Hello, everyone. My name is Nabil Rahmatullah. I'm a fourth going on a fifth year PhD student at Northwestern. I work on automating follow-up of fast transients. Unfortunately, we don't see any kilinovae, so it has to be supernovae. We've heard a lot of times this week about early time phenomena in supernovae, things like shock breakout, but these are really, really hard to find. There's this underlying issue in our workflows, which is latency. And so we had gone through this ourselves in some of the workflows and some of the modules between the first detection of a new supernova by a survey and a human actually finding it. There tends to be order 10 hours of latency. And then from the supernova being found by a human and actually getting a spectrum or some follow-up is another order 10 hours. What I've done is I've automated this process of identifying and following up the supernova with AI for that identification and automated TOO triggering. We've gotten this down to order 10 minutes. And so on the right, you see a CDF of the latency and spectroscopic follow-up for nearby infant supernovae. The black line is what is kind of the baseline with humans, and then the red line is what we've done with my automation. You can see we're expediting follow-up by like more than an order of magnitude. So we're starting to get really, really early spectra and more systematically and reliably probing these very early phases. We've also started doing this with Swift. And then actually in the UV, the case is even worse, where typical latency is like 1.5 days. We've gotten this down to just 6 minutes. And so we're going to see hopefully some really exciting early stuff, maybe shock breakout very soon. I think this is also the first case of an AI commanding a space telescope fully autonomously. So really exciting stuff here. Thank you.
Is this some sort of non-deterministic AI, or is this like fully deterministic algorithmic AI?
Yeah, the model is trained and frozen, and so the scores you get if you put in the same input twice will be the same. So it's deterministic in that sense.
What's the biggest part of the 10 minutes?
The biggest part of the 10 minutes. Oh yeah, so that 10 minutes is like from when my trigger is sent to when the telescope responds. And so it's usually just the telescope is doing something else at the time. With Swift, we can stop whatever we're doing and go point. But with the spectrograph we use so far, SCDM, we cannot disrupt the current observation. And so that's where the majority of the latency comes from. We have time on Gemini now, so we can do this with disruptive TOOs. And so we should be able to get that on even further if we can, yeah.
Let's thank Ravi.
Oh God, that's me. Hi all, I'm John. I work with Igor, who all of you met a few days ago, mostly doing spectroscopic follow-up of tidal disruption events, trying to push earlier and earlier and earlier so we can classify them and follow them up with Swift in order to do UV photometry that will determine or will potentially break the degeneracy between the two different emission mechanisms. I've been working on SOAR follow-up for about 9 months, and I've been directly involved with classifying about 17 TDEs. I also, for the majority of my time in graduate school, have been working on this thing called the Argus array, which you may have noticed I didn't shut up about this whole week. Instead of putting any of the machine learning stuff I did directly, I put where we sit relative to LSST and other all-sky surveys, so you can figure out if this fits any of your photometry needs, and I'd be happy to talk about either afterwards.
Not a question, but a comment. That was perfectly brief.
49 seconds.
I had a question, which is, so wait, what are the two mechanisms that you're trying to distinguish with the early time follow-up?
So there is a mechanism that is a reprocessing of an envelope. So basically you get X-rays that get reprocessed into UV optical and IR, or there's UV optical and IR directly from shocks within the ejective stream. To be perfectly honest, most of my job is distinguishing between 1As and AGNs and TDEs and trying to get follow-up very early, mostly using machine learning tools to try to pick them out of the stream. The issue we would have if we were to try to implement something like Nabil just talked about is that we have so many contaminants that we piss off whoever we're slinging Swift at, because we'd be wrong 80% of the time. So also, if anyone really wants a lot of 1A spectra, I have them. I'd love them to be used for something.
What's the Argus first light right now?
2027. That number is possibly going to get pushed up or down depending on some engineering changes that I am not at liberty to discuss. I'm also not at liberty to discuss the fact those numbers may or may not get a little bit better.
Okay.
Hey everyone, I'm Paige. I'm a third year PhD student at the University of Birmingham in the UK. So I've got about 8 months left, which is stressful. But my work looks at the host galaxies of tidal disruption events. On the one side of things, I've been looking at the bulge masses of these galaxies and how they scale with the TDE black hole mass. The idea being that because of event horizon suppression or that limiting Hills mass that we heard about last week, TDEs are really good at probing low mass black holes, which means we can extend the known supermassive black hole bulge mass relationship. The too long didn't read of the paper is that if we use TDEs, they're highly constraining at the low mass end, and so we need a steeper relationship than canonical previous relationships have suggested, which is cool. And we also see that the TDE relationship is comparatively flatter, and we know this is because of observational selection effects, so the Hills bias and the Malmquist bias, which is luminosity bias. And LSST is really going to soften that luminosity cut, which means we're going to see even lower mass black holes, which is going to be excellent news for the relationship and also really good for understanding different black hole seeding mechanisms. The other side of things is the star formation histories of these galaxies. So we know that TDEs prefer unusual hosts, or these like post-starburst galaxies, and we want to see if we can identify that in their star formation history profiles. While doing this, we've uncovered this like interesting result, which I'm currently trying to write a really quick letter about, but we found a population of low mass quiescent galaxies using TDEs, which is different to what we'd expect. We'd expect high mass galaxies hosting high mass black holes to be quenched because of AGN feedback, but this can't be the case in these galaxies because they host black holes that are too small. So stay tuned for that.
Who are you working with at Birmingham?
I work with Matt Nicol, but he's at Queen's now. And I also work with Sean McGee, but he's like galaxy evolution side of things.
Yeah, so these low mass galaxies, do the TDs look any different from the ones in the more massive ones?
Yeah, so the ones up here are the high mass regime from Cormody and Howe. And then these kind of, it's hard to see, but on the slides, the ones that are starred are the TDEs. So this is kind of where the TDEs start. And you can see we'd expect it to be like red and blue, which is what we see for the most part. But then in the TDEs, we see this flip back to red. We found that a high fraction of these red ones here are like known post-starburst galaxies or E+A galaxies, or even I think it's this one and this one are both in like currently merging systems. So we think it's an environmental quenching mechanism basically that's doing this.
Hi everyone, I'm Anna. I'm going into my final year of my PhD at the University of Portsmouth, and I actually work on something we did not get to cover in the summer school, which is lens supernovae. So I'll try to do it justice in the 1 minute I have. So in this very nice diagram that I wish I'd made, we see that galaxies and clusters in the universe are perfect natural magnifying lens to observe background sources. The potential of these galaxies or clusters deflects the light from background sources so that we get actually multiple images of the same source. These multiple images are magnified or demagnified, and if we have a time varying source, they also appear at different times, which is very useful if you're interested in cosmology. But I won't mention that because I know most of you aren't. But what we can do with this is actually study objects that are further away. And one of the things I'm interested in is also testing some kind of redshift evolution, particularly of type 1a supernovae explosions. Right now, we're limited in our ground-based telescopes by the depth of our surveys. Here we see for the Brighton transient survey of CTF, which is how we discover the one lens supernova found in CTF, we only are able to detect lens supernovae that fall into this really high magnification regime, which is in the distribution tail of the actual magnification distribution we get from lensing. Whereas with LSST, we'll be able to probe objects that follow the natural distribution of strong lensing. So my PhD has been involved in all the process of finding lens supernovae in LSST, from like forecasts and rates of how many we'll be able to find, and also real-time searches in CTF and tests on LSST simulations. I think many of you could maybe benefit from searching your using lensing to maybe try to find your favorite transients. So I'm more than happy to talk about this. I will be leaving on Friday, but feel free to send me a message. Yeah, that's me.
Are there like other transients that are frequently detected through lensing?
So for now, the only one, well, depends what you work, like I focus on ground-based surveys with JWST. There's been a couple more like core collapse supernovae found. For ground-based, all we found is a couple of type 1a supernovae, but we expect actually core collapse supernovae to be the like to have similar rates to lens 1a supernovae with LSST. I did get some rates for TDs and kilonovae, and we might find hopefully one in the 10 years of LSST, but yeah, you can really lens any transient, and the time dilation helps you maybe stretch those light curves and give you more time to study them.
Yeah, I guess the difficulty is that the way we find these things is that you find a overluminous Monet in a galaxy.
Yeah.
And that's only possible because we know exactly what one is looking like. Core collapse supernovae are way more diverse than one is. So even if you found a lensed core collapse supernovae, you're like, yeah, sure, it's a more luminous core collapse supernovae. One is are very standard. Okay.
Hi, everyone. I'm Xiao from Florida State University. I work with Professor Eric Xiao. Basically, we're interested in supernova, the progenesis, the explosion mechanism of it. Recently, I'm working on the interaction signature from the type 1a ejecta and its companion star. So I try to constrain the progenesis, which is from like single degenerate scenario. Generally, we are observers, so we do follow-up observation, and we use Swope telescope and the Magellan Bar telescope, so we can do photometry and the spectroscopy. Sam, if your telescope broken, let me know. We can take it up for you. Yes, we are in collaboration, CSP collaboration, which is Carnegie Supernova Project. Its current phase is called VOICE, which is precision observation of infant supernova explosion. So we are interested in very young supernova. And so far, mostly our targets from DTF and Atlas alerts. So we are looking forward to LST alerts. Yeah, that's it.
We'll start collaborating.
How do you do your fire reductions?
Great question.
Yeah. We should talk stuff here.
Yeah, my advisor told me there are only 3 people in the world can do fire reduction.
I think one of them might be a postdoc in my group, but yeah.
Yeah.
But we're trying to find a new way when she leaves. Yeah, Sahana, yeah.
Yeah, and also he right now is training me to do that. One question is because we the requirement is you need very old Mac. Otherwise, you cannot do it.
Hi, I'm Taya. I'm doing my PhD at Tel Aviv University with Udinakal. And I'm currently thinking mainly about CSM interaction. But generally, I like the description of I work on Shocky and Jetty systems. So, I mean, we've already seen this. I have a lot of transition. You know, basically the idea is you have a star, it has some sort of a wind, and then when a supernova goes off, it drives like a forward and reverse shock system into that wind. Both of these shocks are generally at X-ray temperatures, but kind of on their way to the observer, we may not end up seeing them in X-rays. So basically, if you think specifically, for example, of the electrons in the downstream of the forward shock, those electrons are being heated by the ions because we don't know how much energy the electrons actually get when they pass the shock. These electrons are what's emitting the X-rays, but to emit the X-rays, they need to be heated to an X-ray temperature by the ions. At the same time, they're being cooled by free emission and also by inverse Compton emission from previous X-rays that have now been reprocessed into optical and can cool them in inverse Compton. So this is why the system is pretty complicated, even when you take the kind of spherically symmetric uniform wind approximation. So I'm sorry to all the observers. I am like clumps are way beyond our abilities at the moment, and asymmetries and stuff. But basically, you can kind of get a phase space of the different ways these things look. No, I need another 10 seconds, okay? Where, yeah, the fraction of the X-rays from the shock will actually be observed can change very significantly. One very exciting part of the space to me is that there is a part of the phase space where the electrons and the ions cannot couple by Coulomb collisions within a dynamical time. And that means that X-ray observations of that part of the phase space can potentially tell us something about kind of the microphysics of the shock and how well electrons and ions actually couple in plasmas. Yeah, okay, that's it. Yeah.
What's that line on the y-axis? Like, what's that? Is that speed special for some reason? Like the horizontal line.
That's a time scale where, under the assumptions for which I made this plot, the free cooling time and inverse Compton cooling time are comparable. So it's basically, yeah. We can talk more about this later. Cooperating with me.
Hi, I'm Ricardo. I'm a grad student at UC Santa Cruz. And very broadly, I am interested in transients that arise primarily from interactions between stars and objects around them, such as their planets, other stars, or compact objects. Some of the things that have interested me the most recently are mergers between stars and their planets. Here's an archive link to a paper that we submitted recently, where we studied an event that was discovered a few years ago that is maybe the first observed star-planet merger. And I think one of the most exciting conclusions from that was that you probably need a very massive planet to power this transient, something of order a few Jupiter masses. And also that it is difficult to power this transient in the same way that you can power some of the star-star mergers, which is a dynamical episode of mass ejection plus hydrogen recombination. I think one of the things I'm most excited about with LSST is that they will discover hundreds of stellar mergers per year. And I am very interested in making light curve models that can help us connect those light curves to the properties of the ejecta. And then maybe using hydrodynamical simulations, we can connect the properties of those ejecta to the properties of the stars that emerge. And I think to this end, a lot of the related lectures have been really, really helpful to me, and perhaps, also, and maybe even more importantly, the lectures that have been about things that I do not work on. And I benefited a lot from the wide variety of people and interests and expertise in this room. Just seeing how we all approach and think about problems that we work on has been super enriching, and I feel like those conversations have increased my understanding and appreciation of our shared field. So thank you for that.
Any questions? Yes.
What is a thorn Zitkow object?
Oh, it's a hypothetical type of object where you have a star, but it has a compact object at the center. And one of the possible formation pathways was a merger between a star and the compact object, where the compact object did not have enough orbital energy to eject the envelope of the star. So so another grad student in our group did a simulation of one of such mergers and tried to estimate if it was a viable pathway.
Let's move on.
I'm Natalie LeBaron, grad student at UC Berkeley, and generally my interest is in the near-infrared behavior of energetic transients. So that includes some projects I'm working on searching for signatures of our process nucleosynthesis in collapsars or 1CBL supernovae. Hopefully finding these nice lines that were simulated, maybe. Along the way, found some very interesting objects with dust production. And on the other side of things, I'm very interested in pulling up fast transients like LF bots, and especially in the near infrared, also optical. And the prototypical LF bot, 18 cow, which we learned from last week, showed this access in near infrared, and it'd be cool to find that in more LF bots. Day to day, I do a lot of observing with basically any, mostly near infrared, but also optical telescope that will give me time, both for my own work as well as for things like classifying TDs for the group. Really looking forward to Rubin Discover Transients, and really glad to be able to come to this school and get a better appreciation for more kinds of transients. So thank you, Shelley.
That's a simulated spectrum, right?
Yes.
Yeah, okay. I was like, what lines are these? They were serious lines.
Yeah.
Okay.
I have a question.
Yes.
At what phase in the transient would you expect for these lines to become visible, potentially?
Definitely has to be nebular. Probably pretty deep into nebular phase, but yeah, definitely after nickel.
Hi everyone, I'm Jasmine. I'm currently a PhD student at Swinburne, which is in Melbourne at bottom of Australia, and I'm originally from New Zealand, which is actually to the right of Australia, not underneath it. But anyway, what I'm interested in is how the dynamics of dense stellar systems sort of affects our stellar transit populations. So when you have a big dense stellar system, you've got lots of stellar encounters, and these can affect binaries and what they're doing and how many of them there are. So you can end up with some interesting things and different rates and so So what I do is I do a lot of dynamical models. So my models do the dynamical force calculations between all the stars and does the stellar binary evolution as well. And the idea is to use these to explain what we see. And ideally, I have other people do the observations, and then we can use those observations to constrain our models and make them better. And I'm excited for LSST because we'll see lots of transients, but also that depth that we're going to get is going to make us let us see those really faint cluster members that we can't see right now. We get a better sort of more complete sample of our Milky Way star clusters. So yeah.
Yeah, I'm curious, what are those models, like n-body simulations? Like what are you doing?
Yeah, so I'm doing n-body, so direct n-body simulations with a code called n-body 6++. So it's a direct n-body, so all those individual force calculations. So they do take time to run, and then we use SSD and BSE to do the stellar binary evolution. To do the stellar binary evolution at each time step as well. So.
I'm subbing in for Mitchell. He asked me to do this for him. Yeah, he's on the train or something. But yeah, I guess I'm also Mitchell Carmen. I'm a grad student at Johns Hopkins Space Telescope, working with Subi Gazari, who you saw give talks last week. Mitchell works on TDEs at high redshift, so he found a TDE candidate at high redshift recently. Well, I think they may have now realized it was a superluminous supernovae, unfortunately, but anyways, he does all these things, tries to link TDE rates to supermassive black hole seeding growth models. Yeah, he found the candidate. And then, sorry, that wasn't meant to be dismissive, but I'm saying and then he also forecasts rates of TDEs in upcoming surveys like LSST and Rubin, and he's updating. So he had a white paper on the rates with Roman, sorry, not Rubin. But he's updating that now, assuming a redshift evolving IMF, so there'll be updated estimates for that. And then the last thing, I think that was meant to be a joke from him. I think he really appreciated the summer school, though. I'm not sure how pirates have anything to do with it. But, yeah, it was a great summer school, and we all learned a lot. So yeah, thank you. But yeah, I maybe can answer a question.
Questions for Mitchell.
How did you grow so tall and
Hello everyone, I'm Ken from Harvard Smithsonian Institute, and my work mainly focused on researching the AGN variability using machine learning method, and there are three directions I'm currently working on. So I'm doing the simulation-based machine learning, which means the training data I'm using now are based on the simulation. And the model I'm using now is simple temporal model that drives the X-ray variability, and then also modeling the accretion disk using the reverberation mapping. So the left-hand side is the light curve I have already done on simulations. And then I also use the attention neuron processing model to try to understand the correlation, the temporal correlation of the light curve and the correlation between different light bands. And this gives us a very rich information about what's the information that the accretion, the physical parameters of the accretion disk. And so that is our third goal, and try to infer the accretion disk physical parameters. And another goal is that we want to use that attention neural network to reconstruct a light curve that the LSST might have seasonal gap, and use that machine learning data to reconstruct that. Yeah, so that's broadly speaking my research. quick question. Are these real LSST cadences? They look a bit densely sampled.
Oh yeah, so these cadence are the cadence pulled from the LST, but the line curve here is the simulation based. So we simulate the line curve and apply the LST cadence to mimic.
Okay. This is a very long time period. That's
Yeah, it's 5 years, like cadence.
Okay. Right.
Hello, everyone. My name is Lily Michelle. I'm from Ecuador, and since 2013, I'm living in Argentina. And more recently, I'm doing my PhD in the Universidad Nacional de La Plata. In more general words, I'm working with hydrodynamic modeling of GRB supernovae. I've been working with this supernova 2023 PEL that is associated to a GRB, and this was a very bright supernova, and also like filling the gap between long GRB supernovae and superluminous supernovae was a very interesting object. We proposed a magnetar to model that supernova. That's the QR code if you want to see more information about it. And more recently, we're working with supernova 2025 KJ, and that is very similar to supernova 2023 PL. And that's the QR code if you want to see also. Also, I'm a member of the SOS group, Supernova Observations and Simulations in Argentina. And well, I am now like the link between what observational members of my group does and what we can do with LSST very soon. Yeah, that's it. Thank you. Gosh, I don't know if you all have questions.
What do you use for the hydro modeling?
I use a hydrodynamic code that was developed by my supervisor, version 2011, that is a 1D Lagrangian hydrodynamic code. Thank you.
Okay. One.
Hi, I'm Cassie, a PhD student at Cornell, and I mainly work on luminous fast-fold optical transients, or LF bots. They're mentioned last week. They're pretty similar to supernovae as extragalactic transients with a fairly decent luminosity. However, they tend to fade a lot faster. And LF bots also have consistently strong radio emission, as well as occasional variable X-ray emission. They're pretty rare, so I am currently working on a paper to present multi-wavelength data on a handful of them. And in addition, I help monitor the CTF alert stream to try to look for new LF bot candidates. And when we do find one, I submit proposals or triggers to the Swift Observatory for X-ray data, Gemini for spectra and redshifts, and a BLA for radio.
Questions? Is there a way to do this in like the Atlas data stream, or do you need a specific alert infrastructure to do the filtering?
I think Atlas is theoretically fine. It's just this, you kind of need a sensitivity of CTF because they're pretty rare, and we also need accurate color information to make sure they're blue. And sometimes with Atlas, it's a bit tough. The error bar is going to be large.
Okay, let's move on.
Hi everyone, I'm Cassidy. I'm 2 years into my PhD program in Tasmania, right at the bottom of Australia. Pretty much my PhD is trying to find more kilonovae, and as you've heard over the last 2 weeks, that's been really, really fun. And by fun, I mean incredibly frustrating. I started my PhD about the time that O4 started, so I had such high hopes for gravitational waves. But as it's turned out, my PhD has been more about focusing on GRB follow-up and afterglows. Interestingly, we've heard that kilonovae should be associated with our short gamma ray bursts because those are coming from our binary neutron star mergers, but there has been some evidence in the last few years of high confidence identification of kilonovae candidates with long GRBs, which is not the expectation. So I've been doing some work to see if we can maybe find kilonovae in places we hadn't expected. And part of that's also been developing a bit of a host targeting scheme or tool. So I've been investigating the properties of the hosts of kilonovae because we do have a sample of candidates to whatever level of confidence you want to choose. And so having a look to see how they can be used to possibly differentiate or identify GRB candidates that should have prioritized rapid follow-up. So that's something I'm working on over a few telescopes, but primarily I use the Greenhill Observatory at the University of Tasmania. So they are in Tasmania, all the way down the bottom of the world, and beautiful, beautiful skies. And that's most interesting for LSST because us in the east coast of Australia, among other few other places like New Zealand, are going to be some of the first observatories to be able to do follow-up of LSST alerts. So we're really doing our best to get our facilities up and running for rapid transient follow-up. Obviously, I'm looking for kilonova, but anything cool that I get to play with the telescope, please let me know what I can do with it.
What kind of tools are you using for host associations between kilonovae and nearby galaxies?
So at the moment, the work that I've been doing has been focusing on just some archival data, just looking at what we do and don't know about them. But I'm about to start doing a campaign with LCO to do GRB host follow-up, try and identify hosts, and then look at the properties and see if there is a way to use that as a way to identify the events that should have rapid follow-up.
Follow up on that. I know a lot of short GRBs are they occur off galaxy center or very far from them.
Yes, so radial offset makes that very difficult. It is a very good identifier for shorts and for kilonovae, but of course makes it very difficult if you can't see the host. But there are some other properties that seem promising, such as the star formation rate and the metallicity.
Hi, my name is Nicola Bukowiecka. I'm normally based at University of Rhode Island, but I'm a guest researcher here, so I moved here. So I'm interested in jets, they're kind of how they're affected in theory by space-time geometry, physics models, and gravitational collapse. So in terms of space-time geometry, how they're affected by the nature of the compact object itself, whether it's a black hole or a neutron star, gravitational theory, or type of matter. So when you have non-standard metrics, you can interpret them as a classic or GR, exotic matter, or a vacuum space-time non-Kerr metrics. In terms of physics model, you can use GRMHD, which is, as you know, ideal MHD, kind of infinite conductivity, often test fluid approximation, or you can go into two fluid models where you have first principle derivation from the Vlasov equations models where you have two species, so you can have electrons and protons, which is very important in context of the systems that I'm interested in, which are collapsers, and crucially collapsers with magnetars that may or may not be able to power GRBs. And the last part is the gravitational collapse. So when you have actual dynamic spacetimes. So the questions to answer here is, what is the initial hypersurface that could lead to have self-consistent gravitational collapse with neutron stars? What are the equations of state? What can you actually like how do you so consistently have the gravitational collapse from a neutron star to a black hole? What are the jet properties of both of the neutron stars, black holes, whether they can power GRBs? And then question to you guys, like, what can you give me? And can I make a prediction for you?
Questions? So we just heard a little bit about this long GRB associated with, or kilonova associated with long GRB, which is like against standard paradigm. So do you think this has something, I mean, this probably has something to do with the types of things you're studying. So do you have any hypothesis as to what the cause of this might be when you have a merger that produces long GRB instead of short GRB?
No, not really yet, because as for now, we don't really have a good sense of what is the good prediction of the luminosity from an actual gravitational collapse. Then, when we have a star, we have a core collapse, then the protoneutron star collapses to a black hole, and then we launch jets, they break out, we have the photospheric emission and all that stuff, and then we have GRBs. Like, is that luminosity? Are those GRBs? Do they come from the protoneutron star? Do they come from a black hole? And then that has an impact on the kilonova and on those luminosities. We don't have a good way of modeling right now, even the gravitational collapse with all the physics incorporated. So I cannot answer that question properly. That's what we're kind of doing right now. Yeah.
Okay. Okay, we'll move on. Alex.
Hi, I'm Alex. I'll start with my praises school to get my extra minute, or maybe I can have Anna's time. No, I'm kidding. But it has been a really great experience. I'm based at Columbia and also at the American Museum of Natural History. I'm going into my 3rd year, and I'm really interested in interacting binaries, which has manifested in a lot of work on systems that produce nova explosions. So everything Mike talked about, basically. Calculus variables and also symbiotic stars. So it's been really fun to be here and get to learn about a bunch of different types of extragalactic transients, which I did not know that much about the physics of before. But just to talk a little bit about the work I've done, Mike didn't get to tell you about the Condor Ray telescope, aside from in passing, but this is a small telescope in New Mexico. It's made of 6 off-the-shelf 6 to 8 inch telescopes with attached CMOS detectors, and what it's really good at is measuring really, really low surface brightness stuff, but it's also really good at taking pictures really fast because it has low read noise. So last fall, we used it to take 1-minute images of Andromeda. And sorry, for context, the field of view is also really big because of the format of these cameras. So we can fit all of Andromeda in one field of view. We took images every minute for 3 months, every time we could point at Andromeda. So this is a really cool data set. And what we're looking for is the earliest stages of nova eruptions, because like Mike said, we have 50 novae in Andromeda every year. So over our couple of months, we got at least 6 of them, possibly more that we haven't found yet. And you can see here that I'm showing the emergence of one of those novae close to the center of the galaxy. We're hoping to do that again this fall. I'm actually going to New Mexico next week to add some more telescopes to Condor and hopefully not break it, but stay tuned for that. And then my other work, I'm starting to do a project with Kishore where we're going to be looking for symbiotic stars and ZTF light curves by looking for Mira variables that have unusual dust production events. And I've also done some modeling work with MESA about time variable accretion onto white dwarfs. So this is all kind of tied together into these white dwarf and evolved companion systems. I will just add that I'm excited about LSST.
Can you speak to the physical mechanism on the precursor to the nova, as you call it?
What do you mean by precursor? Oh, like what happens before? Yeah, I think it's very similar to all the types of transients that we've heard about where people have been saying like, oh, we expect there to be some early UV flash. That's the same kind of thing that we're expecting here, is that in the nova, as the white dwarf undergoes this thermonuclear runaway, before it puffs up to the point where you're getting the optical radiation coming out, you should be able to see it brightening in the UV and X-ray. Condor is on the ground, so we obviously can't capture that. So instead, what we're looking for is, I mean, first, just the early brightening in the optical is interesting because no one has been able to measure that with this type of resolution. But we're also using a U-band filter to maybe catch some of that UV flash. And then we're also looking to see if there's signs of interaction with the companion star in H alpha or helium too. Well, I didn't mention this either, but Condor primarily focuses on narrowband imaging. So.
Quick follow-up.
Yeah.
What is like the time scale of that early flash?
Great question. We don't really know. That is what we're trying to constrain. Short though. I mean, because novae tend to be like hours to days in terms of their brightening, so this should probably be shorter than that.
David, do you have something really quick?
Yeah, I was just wondering what the like cadence you would need in U-band to find the kind of variability you're looking for symbiotics.
Yeah, the thing is that if you go too low, you're not going to go that deep, and U is not that sensitive. So we've been using 1 minute, and it honestly looks like that's not deep enough. So there's a balance that we haven't quite figured out yet. But the benefit of Condor, since there's 6 of them, and hopefully soon to be 8 of them, again, stay tuned, you could use the U-band on multiple telescopes and go deeper. So we're still working that out.
Okay, so hi everyone, I'm Vidisha. I'm from University, and I'm one of the few people here that are interested in AGNs. So I'm studying changing of AGNs. Just a reminder, these are objects that change, transition between a high state and a low state. So the broad emission lines in the blue continuum kind of disappear or appear. And we think that these are triggered by some changes in the accretion flow, but this is somewhat in tension with the accretion disk theory that predicts that these changes will occur on much longer timescales. So I'm looking for these objects in repeat spectroscopy surveys, mainly at DSS5. I'm doing follow-up spectroscopy, studying the statistical properties of these objects and the host galaxies. But the main observational challenge with these objects is that we usually only have 2 spectra of the high state and the low state. Ideally, we would want to have optical spectra during the transition and also trigger X-ray observations to study the innermost region of the accretion flow. So I'm really hopeful that LST will help with early detection of these objects so that this will trigger follow-up observations to get hints into what happened there in the accretion flow. So if you find any highly variable AGNs, don't hold them out. You can send them to me.
So what is this plot showing? The black.
This is the
M sigma with changing look AGN on them, right?
Yes, we find that changing look AGNs basically follow the Fourier correlation of inactive galaxies. Generally speaking, the host galaxies look exactly like typical AGN galaxies, so it's probably not environmental. That's what we find so far.
Okay. Move on.
So hi everyone, I'm Xin from Columbia University. I'm a second year grad student, and my interest is mainly about the neutron star simulation with MHD or molecular dynamic simulation. So I'm currently working on the glitches and neutron star glitches. On the top left floor, you can see the rotational frequency of the neutron star versus the time. So normally you would anticipate that the neutron star gradually spins down because of like energy loss or axial torque. However, you do see some glitches like sudden spin up in this rotations, which is very weird. And we are going to understand that and modeling the interior structure, like how the vortices in the superfluid, the neutron star coupled with the crust of the neutron star. So Well, it might not produce transients for the normal neutron star. For magnetars, its large bridges can produce X-ray burst, and it might cause some transients that can be observed. And another project I'm working on is about the neutron star accretion column. So you can see that in a binary system with the neutron star and the companion, the accreting material is followed from the accretion disk and it's guided by the neutron star magnetic field and accreting on the pole of the neutron star. And this pole, like we are simulating this pole because they will form an accretion column. And it's actually the model that why we see pulsars, like why we see pulsating effects. And it also explains the pulsating ultraluminous X-ray sources we might see. And our model can also predict the lecture, the lecture from these pulsars. And I would like to thank you, Kashi, for organizing this summer school because it's totally new for me to learn about transients and all the observation. And you can see might not be highly connected, but also on the other hand, I believe that our model might have something to be observed, and also our simulation can explain something you observe. So I'm happy to talk with about related observation and simulation if you are interested. Thank you. Yes, please.
What code do you use? And follow up, what's your neutron star model?
Oh, so for the interior, we are using the LAMPS, the molecular dynamic simulation. For the accretion column, we are using the Athena, like the MET simulation. Yeah. So, and for the follow-up question?
What's your neutron star model?
A neutron star model.
Yeah, how do you model a neutron star? Is there a black hole with some boundary conditions, or is that like how do you model a neutron star?
Oh, we are modeling it like for the first one, we are assuming like a microscopic small level, like 10 to the negative 15 meters, and we are using the molecular dynamic simulation. Probably superfluid is a classical model basically. And in the second model, we are doing like a column, like a Cartesian column, and you have a accreting matter follows from the top and accreting to the pole.
Right. Okay.
All right. Thanks, Zin. All right, I think that's it. Okay, so hi, I'm technically a 9th-year PhD student now. But anyway, I'm not going to go into talk about this. So this is supposed to be an example of what these slides were going to look like. Okay, so right, so we are end of the session. As you saw, we've had a very large diversity of scientific interest from NSST and expertise, theory, and observational, and that was kind of the point of the way we tried to design the school, which is get people together who normally, let's say, do not meet at your topical conferences, and especially early on, and get you all to start thinking and about the overlaps between your science, and hopefully together construct something that that will make this data stream much more rich in science. So but just as a ending note, all of us had fun the last couple of weeks, but really the hope is that you can go back to your home institution and spread all of this knowledge that you learned from the schooling. Right here, we've been fortunate to sort of be able to interact with the lecturers who've been really doing cutting-edge science with this, but go back, share the materials. All the materials will be publicly available. We should be sending out the link early next week. So yes, share it. Oh, okay. Yes, yes, recording slides, everything. So share it with others who are interested in SSC science. If you have questions, hopefully you're better positioned to answer those questions because you've been at the lectures directly.